Can people online hear me?
Yes.
Thank you. Start in just 1 second.
I'll keep chat stuff.
Perfect.
YouTube chat, if anyone happens to use that.
Oh, I'm going to tell you. Can people online hear me?
Yes.
Thank you. Start in just 1 second. Oh, it's the live stream. That was scary. Good morning.
We're also streaming to live to YouTube. That's good Lord. Okay.
Hey, everyone. Just trying to find my bearings. Share. PowerPoint. And then let's just do this. Okay, can people online see presenter mode or the normal mode? Beautiful. Presenter mode. What about? No, but then that puts that backwards. Why make it just do only slideshow?
Yes, I can see.
Sorry, say that again. You slideshow. I think I see it. Did it? Is it working now? Yay. Okay, cool. All right, let's go ahead and get started. Hey, everyone. Oh, hi, Nick. Welcome to the PyHC 2024 Summer School. I'm Julie Barnum. I'm the PyHC PI and lead. In the back over here is Sean Polson. He's the PyHC tech lead, and we are the two in charge of running this show. So if you need any help, find one of us or any of the wonderful package leads that you'll be meeting over the next couple of days. So without further ado, I was going to start with a quick intro to PyHC, just a few slides for those who aren't super familiar with us, and then just some housekeeping and general summer school agenda things. And I'm not keeping an eye on the chat, so Sean, I'm assuming you'll handle that. Beautiful. All right, so PyHC, who are we? We're the Python and Heliophysics community, and they have 4 basic tenets for how we want to be. So the first thing is that we promote the use and development of sustainable open source Python software within heliophysics and space physics. We work to improve communication and collaboration between disciplines, users, and developers within those disciplines as well. We establish and maintain development standards for code submitted to our community, and then we foster interoperability and reproducibility of science done with the packages in our community. We've always been and still are and probably always will be a grassroots effort. It all started at a conversation at the American Geophysical Union, AGU, which if you haven't been is an annual conference where all the earth sciences and space folks and so forth get together. But it was a conversation between my old boss and then the guy that I work with at NASA now, Brian Thomas, his old boss. And then before you knew it, we had a session at another popular meeting amongst heliophysicists tests. We got a small grant from NASA to start running the show and organizing, get-togethers, biannual meetings, telecons, that kind of thing. And now we are the community that we are now fully flourishing. The organizational structure, I already kind of hinted at that. As far as leadership goes, it's just me and Sean. We're funded by a NASA grant in order to help lead and organize all of these things. We technically don't have a steering committee. Whenever we first started, we were pretty small, so that just wasn't necessary. Maybe that'll change in the future. But we do have a lot of people within our community. This is just a small snapshot of some of the GitHub profiles of people who are involved with PyHC. We are not just one package, as you'll come to find throughout this week. That just didn't make sense based on all the different requirements and needs of the various subdisciplines within heliophysics and space physics. So we have several packages within our community that all work together instead, and we're constantly trying to improve that. And we consolidate effort where possible, so try to avoid reuse and duplication of too many functionalities. As of right now within PyHC, we have 83 packages, and I'm pretty sure that's accurate. We haven't had another one submitted in the last 2 weeks. We have them split up into what we call our core packages, which are what you're going to see presentations from all this week. And those are wide in range and functionality and widely used within the community. We also have a couple other levels of packages other and then unevaluated, and that just has to do with whether or not they've looked at our standards and made grades of how they're doing against them. But neither are any less important. They're just usually more specific in what they do and so forth. And you'll hear from one example of one of our other packages, that's Magical Web. Pretty sure that's tomorrow. And the domains covered by our packages kind of range from the sun to mud, if you will. So solar, heliospheric, the geospace sciences, aka magnetosphere, and then ITM or ionosphere, thermosphere, mesosphere physics. And our packages have a lot of different capabilities, from analyzing model output, a little bit of machine learning in there, a lot of data visualization analysis, data wrangling, that kind of thing. So without further ado, moving on to our summer school agenda. So day one, this is where we are right now. I didn't include my intro talk in this bullet, but we're going to have a lovely plenary talk from Alex over here. He'll be up in a minute to come and kind of set the scene for, open source programming and why it's important. Peter will come up and give a HelioCloud intro so that you all know how to use this platform that you're going to be using in order to follow along with all of our notebooks and tutorials. And then we'll just get started right into the core package introductions. We'll start a little bit with AstroPy, technically not a PyHC core package, but a lot of our packages leverage that package to do various things. And that'll be presented by the folks that are going to be doing SunPy, and then we'll have PlasmaPy. And tomorrow we'll wrap up with the rest of the core packages, as well as adding on Magical Web. Day 3, we'll have some discussion on different ways that PyHC packages and other highly used packages in PyHC do time and coordinates. We'll have some how-to sessions for various important things you might want to do doing open source software programming and so forth. A panel session where you can go and ask, all of our wonderful developers questions and whatnot. And then we'll have some posters. Day 4, we'll move on to multi-package use cases, so how different PyHC packages can work together. And then we'll have a really fun PyHC challenge ladder activity that Sean and others have been hard at work organizing, and there will be prizes, so get excited. And then the last day is going to be a shorter day. There'll be like a séjour into machine learning and heliophysics, a quick kind of advice for searching for data within heliophysics, and a wrap up. And as a reminder, lunch is on your own. We do not pay for that. There's a lot of options, a really close driving distance. I advise either carpooling or, getting with one person that has a car and maybe getting all your orders with that person ahead of time. But yeah, we can talk more about that later. Some extras. So tonight, chill, go back home and rest. But tomorrow afterwards, if you're interested, there's going to be a self-sponsored, aka you pay yourself, reception at Avanti. And I'll put the address for that in Slack in the social channel. So if you haven't joined our Slack, do so. If you need the link to do it, just come and tap me and let me know. Day 3, there will be a self-sponsored fun activity afterwards, either an escape room or axe throwing. I don't yet have the sign-up sheet, but I will after lunch today, so you can come and start putting your names down for what you're interested in. And then day 5, after we wrap early, so long as the weather cooperates, we're going to have a hike after lunch, and I'll throw some options in social for that as well. Just the mandatory summer school etiquette. You all, whenever you registered, said you would follow the PyHC Code of Conduct at all times. So just a reminder of where that is. If you go to pyhc.org, you'll be able to find it in the document section. If you violate that, we're going to kick you. So be a good person. Zoom, please don't share that link with anyone else. It's not a part of the summer school. We have a limit of 500 participants, so I don't want to blow it up accidentally. And if you are on it, please stay muted if you're not asked to unmute to ask your question. If you have any issues or questions with HelioCloud, Peter is right here and is your in-person representative for that. If you haven't logged into Slack, you should, because in tech questions, people can also ask questions there if they're online or technically in person too. For presentation questions, for those of you online, there's the Q&A feature on Zoom. Please use that to ask questions about the presentation, and don't just throw them in the comments section so that it doesn't get lost in translation. As far as in person, we have this microphone, and then Sean has another, and we'll be passing them around, so you can just raise your hands. And if you have any non-immediate questions, aka non-real time, within Slack, there's separate channels for each of the packages that you can go through and ask, further questions if you have them after the presentation wraps. And for any general summer school questions, you can always put them in the general channel on Slack, or you can email PyHC confidential LASP Colorado EDU, or just shoot me an email. And I think this is my final slide, so miscellaneous. I think you all probably already handled it, but if you're here in person and you haven't taken care of your parking pass, if you have a car here, go back to the front desk and do that. You will get a ticket, and it's very annoying. The restrooms, you're going to go back out the hallway and walk all the way to that end of the building, turn right, and it'll be like one of the first few doors on your right. Lunches, again, I'll get a sheet out for signups, but if anyone's willing to volunteer as tribute for going to get food and or carpooling people, please let me know so we can get that organized. And if you're a social media user, use the hashtag PyHC School 24 so that we can get some cool pictures collected for after the fact. And there will be stickers at the front. We have some stickers to pass around for HelioCloud, and after lunch, I'll have the ones for PyHC. And that is all from me. I believe next up is Alex.
You, Julie. Let's see here. Where is presentation mode? Yeah. Oh yeah, okay. All right. Can everybody see that online? Hopefully.
Yes.
Awesome. Thanks. Well,
Yes, I can see your slide.
okay. Thank you. Hi, I'm Alex Kouthos. I'm a research software engineer at Stanford University working at the JSOC. So if you've ever gotten any of the SDO, Solar Dynamics Observatory data from AIA or HMI, those are coming through us. I'm also a steering committee member at the USRC, which I'll talk about a little bit later. And today I'm going to be talking about software best practices for reproducible open science. All right, got to figure out which is the right buttons to press. Okay, so I'm going to be kind of starting off with a discussion on reproducibility, which is one of those key tenets that Julie just mentioned for PyHC. We'll then be talking a little bit about some software best practices, including these three specific ones, and then talking a little bit more about some other options and just other resources that you might be interested in. If you're interested in following along, there is a poster version, which you can get from this QR code. I'll also be sharing this at the end, and I'll also have a poster up later this week on this same one. So if you have any questions, definitely come talk to me on that. All right, so let's talk about reproducibility. So over the last 2 decades, we've had a lot of concern about how reproducible science has been. One of the more notable studies that was done in 2016, it was a Nature article where people surveyed over 1,500 scientists in various fields. And what I'm showing here is a figure from that discussion. And you can see it's a little bit hard to wrap your head around without like actually looking at this a little bit more. But essentially, the widest bands that you see on the graph there is about 25% of the respondents in a specific field. And so what you mainly get out of this is that both in a lot of the fields, there's kind of a mix on whether or not people believe they'll be able to reproduce work in their field. And in chemistry and physics and engineering, we seem to be more confident than others in the ability to reproduce. There's more than just one study on this, so this is not like, this is a pretty common concept. But in reality, these expectations don't quite meet what we would like. It's actually almost, in some sense, anti-correlated here. So in this figure, it's actually the larger numbers or the more red you see on these graphs, the worse it is. So this is the reproducibility or the number of failed attempts in reproducibility, or the percentage. In the dark red is people being able to reproduce others' work, and in the lighter red is being able to reproduce your own work. And as you can see, in the physics and engineering space, we actually, about nearly 70% of people have failed to reproduce others' work. What makes it even worse is about 50% of people are unable to reproduce their own work, which is pretty telling. So we are, so like this concept, it has been come to be known as the reproducibility crisis in the sciences. This, again, has been around for a little while now, and it got some more national attention. I'm sure people have, talked to others about the public's trust in science in general recently, but Congress even took note and actually tasked the National Academies of Sciences, Engineering, and Medicine to create like a task force and look into this problem. What they ended up doing was, in 2019, they came out with a report that has a lot of really good information on it. But right here, I'm just mentioning two of the specific things that they did or that they defined, which was what they mean by reproducibility, which is, in their words, also just known as computational reproducibility. And this one I'll read directly, but they define it as obtaining consistent computational results using the same input data, computational steps, methods, code, and condition of analysis. They also define replicatability, which is kind of more of not using the same data per se or the exact same methodology, but trying to answer the same scientific question and coming up with similar conclusions. So today I'm going to be talking specifically about reproducibility and computational reproducibility, and how we could potentially help with this issue. So I'm going to be talking again about three best practices, software best practices. One being version control, the other being code reviews, and the last being documentation. These obviously help with reproducibility. Otherwise, I wouldn't be talking about it. It also helps with a bunch of other key goals, scalability, so being able to kind of like start from something small and growing to be able to do more. It really helps with collaboration, being able to communicate with your peers and working on things together. It boosts clarity. It helps with transferability, both in terms of like sharing data and your packages and everything, but also in transferring knowledge, which is really important. And then it also helps with transparency, which will help with people's trust, both scientists and the public. And then I won't really be touching about this too much, but it also can help with reusability of code. So like being able to reuse certain parts of your code in different places. So what is version control? I'm sure we've all done some form of version control before. Here I'm showing a figure from PhD comics where you start with a final, let's say your dissertation defense or something. And you then go to your advisor and you go back and you have to rewrite it and you name it, okay, final version 2. And then you do this 6 more times and then 10 more times. And then the next thing you know, you have some ridiculously long file name. So this is a form of version control. It's obviously not very useful because you kind of have several documents that are more or less identical with minor changes in between. But version control is really just tracking the history of something over time. In our case, it's mostly going to be software, but you can use it for other things as well. If you've ever used Overleaf, which I would suggest if you're using LaTeX documents, that is also version control, or Google Docs, if you've ever used Google Docs or Microsoft's stuff. Again, this obviously touches on reproducibility and several of the other key goals that I was mentioning before. What I'm going to specifically talk about is Git. For those who haven't used Git, it's by far the most popular version control system now. There are, I think it's 95% of people use Git for version control. And it was developed by the Linux founder or main author and contributor, Linus Torvald. And the idea here is that you're just tracking your changes via these things known as commits. Commits are essentially just snapshots of your repository, the repository being this full history. It's just a snapshot in time of those changes. And what I'm showing here is kind of like the simplest way you could use Git, where you start with, let's say, something on the left-hand side of this figure, just an initial commit, and then over time you make some changes, you commit that or save it off as a snapshot, and that becomes another one of these circles on this graph, and then you do the same thing again, that becomes another, and so on and so forth, and all of a sudden you have this linear history of all your changes, and things kind of point back to what they originally had come from. And this allows you to really easily track changes between any two commits. Even if they're not directly linked, they're linked in some capacity, so you can make a comparison between what you have in your last commit there and what you have in your first. I'm also bringing up this idea of branching, which is kind of taking the same idea. So you're still doing a history. What you're doing is this main branch. So the simple one is kind of becomes your stable branch, where you want all your code changes that you have like verified and want to like release to the more general public. And then off of that, you can decide, okay, well, I want to add some new feature, let's say, or try some new method out. Well, that you can do this by just taking one of the previous commits, making a new branch, new feature branch, and start keeping history there. This allows you to be more nimble and make changes without necessarily breaking stuff that's already working. Or if you do break stuff, it's not being pushed back to your main stable branch that everybody is using for their work. So also, I'm going to be talking about code reviews here. And so what's the idea of a code review? Well, it's pretty straightforward. It's just reviewing code, but it's generally a process in which you do this review. So again, I'm showing this figure that we had before. You might have been asking, but how do you make sure that what you get into your stable branch is still stable after you've done these iterations in your feature branch? So what you can do is a code review, which is you create some process for actually reviewing the code before you put it back into your stable branch. This way, you know that you have at least tried to figure out any mistakes or track issues that might have come up in your feature that would have broken something in your stable branch. And this process is pretty straightforward. It's just 3 or 4 steps where you start with just making some updates to your code on this new branch. You make those changes, you commit them. You do that several times until you feel comfortable with your code where it's at, and you think you want to put it back into your main stable branch. So you make in GitHub, it's known as a pull request. GitHub is just a space that allows you to do all these various software best practices with Git kind of being its base. It's a place to host your Git repositories and then do all this. Anyway, so you will make those changes, you'll make a pull request or a merge request, and you try to get those changes back in. That kind of triggers this idea of a code review. So you'll either review it yourself, or if you're working with a team, you have somebody else review it. And I always suggest if you can have somebody else review it, this is probably going to be best, even if they're not necessarily an expert on your code. Just having another pair of eyes on something can really find issues before you push them into your stable code. And then if they or you have any suggestions, you'll have a discussion on that. If you need some changes, you'll start kind of go back to the top, make some changes, commit those, push them, review again. And then once everybody's comfortable with it, you okay it, and then you just merge that back into your stable branch. And so this whole process is just known as a code review. And again, this really helps with making sure that you're not adding issues or kind of finding these issues beforehand, before they actually come up in your stable code. And so the last thing I wanted to talk about was documentation. And just to take a really quick step back. So the reason I'm mentioning these three things is I feel like they're kind of like the easiest things you can start with. A code review does not need to be something super complex. It can be something simple where, again, just before you decide to make your commits, you just do your own reviews. Git is really easy once you learn how to do the basic functionality. And again, if you're just trying to do at least a stable branch or one single commit history, that's fine. Also, documentation, again, is extremely important. Documentation everybody's used. It's pretty straightforward. Again, it's just some text-based platform for tracking how your code works, what expectations you have for it, how to install, anything you want to share. This again helps with reproducibility, and more specifically, it helps a lot with collaboration and transferability. So again, that idea of transferring knowledge from yourself who knows the code or software really well to others in the area. And so let's look at some forms of documentation. So there's kind of two ways I'm going to mention it here. One is having documentation in the code itself. Here, I just grabbed an excerpt from one of the SunPy functions, the git header function in the fits data, or the fits module. So here, they just have this function, and right at the very beginning, they have these 3 quotes and close 3 quotes where they just put some information, a really brief summary of what the function's supposed to do, what the parameters are or the inputs are, and how you expect those, what you expect those to be, and then the returns for this function. And if you do this and have some system that can then convert these comments into a more friendly version, you get something that's like on the right here, which they just created after taking doing some automation to convert all this stuff on the left-hand side to this right-hand side. Another way you can do it is just putting something at kind of like the root level. This is more like kind of higher level documentation. I would 100% suggest that at the bare minimum, do this. Just write a README file, readme.md. MD is a markdown file. It's a fairly human readable syntax that allows you to just write some lines of documentation like you see here on the left-hand side. And then that will eventually be converted into a more formatted and nicer to read version that you see on the right here. This was just using VS Code's simple conversion. But if you do this on GitHub again or other things, you actually have the ability to have this generated automatically. As soon as you put a readme.md file into your Git repository on GitHub, it will automatically generate a file like this that's much nicer to read. So again, as a bare minimum, I would suggest doing at least the readme.md file. There's other forms of formatting you can do as well. Restructured text is another example, but that's a little bit more complicated. So again, if you're just trying to start out with the easy thing, I say, and then once you get more into this stuff and decide this is really awesome, I want to make things look a lot nicer, then you can look into the kind of other formats. All right, so that's the main three things that I wanted to talk about. But before I move on to total conclusions here, I just wanted to mention some other best practices that you might hear about or want to look into in the longer run. One of those is known as testing. This is, again, a really important thing for making sure that any parts of your code are working as you expect. And so when you're making changes, you can run some tests to make sure that you didn't break already existing functionality. There's this idea of issue tracking. Issue tracking is just, again, essentially that, tracking issues over time. Those can be bugs, new features you want to add, anything. You can just kind of get these little cards that you just keep some information in and use that over time to make sure that your software is following whatever you decide is worth efforts, or the community decides, I found these bugs, can you fix these? Automation or continuous integration and continuous development or deployment, depending on who you talk to. That is just essentially making some of these things more automatic. So when you make a push to your Git repository, maybe you automatically run something like your tests, or you automatically generate your documentation or something along those lines. So this can be really helpful. Again, one of the best things to do is, if you have compilable code, is making sure that one of your key kind of tests here is that your code compiles when you're making a pull request, because if it's not compiling, it's not working. So that's, again, kind of one of the bare minimum tests that you could potentially do, and you can automate that pretty easily in GitHub. And then the last thing I wanted to mention is peer programming. If you have somebody that you can work with, I would highly suggest just occasionally sitting down with them and working on doing some coding together. It's a great way to learn from somebody else, and again, kind of catch problems before they even arise, because you're always going to have like a one-on-one conversation with people while doing this, and you might learn something completely new or realize that you were doing something wrong that they have a little bit better of an expertise on. Yeah, and then there's several others, but I'm not going to go into it now. And of course, all of these help with reproducibility, but also all the other goals that I had mentioned previously. Some resources. So this is by no means an exhaustive list, but I'm mentioning three ones here. One, kind of plugging the United States Research Software Engineer Association, or USRSC, which I mentioned earlier that I'm a steering committee member for. This is a group of people who are research software engineers or allies. Research software engineers are, again, kind of what it sounds like, but they're software engineers who are interested or more geared towards research-related software. There's a ton of resources on here. We have a bunch of working groups trying to come up with more resources, create education opportunities, various things. Kind of not exactly a spin-off off of this, but something that is associated with the USRC a little bit is the Better Scientific Software. I think it's Alliance. They also have a ton of resources. So they're a little bit more oriented towards the technical side of the resources and stuff, but they also offer like fellowships and things for people who are interested in this type of work. So I would definitely check them out. If you want to learn more about documentation, they have a whole section on that. On version control, they have it on that. Any of the things that I mentioned, they have a lot of resources on. Okay, and then the next thing is an NSF-funded, what's known as the Intersect training. It's a little bit late for this year, but I think the applications are all closed. But they offer two things. One is a boot camp for those who are more on the science side and want to learn about software best practices and some of these things that I mentioned. So they will actually, you can apply to that. And if you're accepted, you'll go to Princeton and work with some research software engineers on bettering your skills for that, or learning these skills. They also have one that's a little bit more geared towards people who are already kind of know some of this stuff, but want to expand on those skills. So they offer both. Again, I would definitely check them out if this sounds of any interest to you. Also, if you are interested in the USRSC, it's entirely free to join. So I have on the next slide just the join link specifically. We also have a conference coming up in October. I think it's the 13th to the 15th, mid-October for sure. It's in Albuquerque. This is our second one. And then again, if you're interested in the poster version of this talk, more or less, the QR code's there. And I'll take any questions. Thank you.
And yeah, I can read that one for you.
Okay, awesome. Thanks.
The first question in the Zoom chat we got was back on the side where you were showing the doc strings just for function calls.
Yeah.
And the question was if there's any way, well, I'll just read it verbatim. Is there any way of keeping the variables in the function in sync with the parameter section of the comment? So basically, if you update the code, can it update the doc string automatically?
Yeah. So I'm actually not entirely sure about that answer. These do get a little bit more difficult to make sure are up to date. So in some sense, I tend to like to make sure that you are updating these functions on that kind of like pull request spot so that you're not like constantly going in there and fiddling with adding a new parameter and then realizing, oh, wait, no, that's not the right parameter. I want a different parameter, or I want more parameters. So instead of like getting too bogged down in the documentation in real time when you're working on the software or working on like implementing new things for that software, I kind of like to do these things towards the end. Again, at that review process stage. That being said, is there an actual automatic way to do it? I'm not certain. Maybe somebody else in the room who specifically, yeah, do you have a? Right, so maybe some plugins with your IDEs could help with this. Yeah, that's definitely possible. Yeah, otherwise, I'm not sure if there's anything like inherent. I'm certain, yeah, exactly like you said, there's a plugin that you can use from an IDE. Or, maybe this is a good place for where AI can help, right? If you're using CodePilot or something like that, I'd be a little shocked if they don't help do this in some capacity. So hopefully that somewhat answers your question. Anybody else?
We have one more from the Zoom Q&A, but I will prioritize in-person question.
Hi, thanks for the great talk.
Thanks.
Just had a quick question on, so any tips or best practices for the size of the commits and the size of the pull requests, especially when considering open source contributions?
Yeah, that's actually a really great question. So all this stuff kind of comes down to personal preference or team preference, right? So one of the best things you can do is if you're working with other people, is to kind of figure out what those, what you would like to do for those things. So if you are interested in making sure that your commits are small or a little bit larger, like just have a conversation about beforehand. I personally tend to like to do lots of small commits. So anything that is a change that I feel is useful, I'll just kind of keep it small and kind of focused on a specific thing. So like I don't tend to fix formatting and some code changes, some functionality changes at the same time. I keep those as separate commits. I also, again, try to keep them very focused on one thing and not try to hit, like if you're hitting multiple files that aren't related in any way, not to keep those all in one commit. And then when you're making these feature requests, I also I suggest to keep them smaller. I mean, sometimes they will run larger, but if you can, kind of keep them as small as possible. It makes it much easier to do the code reviews.
Now, I'm going to read the one from the Zoom Q&A too. The question was, how big does a project have to be before you make a GitHub for it or use Git in general? Is this something you're doing for every project or over 1,000 lines or what? Does it depend on the language you're using or how community facing it is?
Also a great question. So again, this kind of comes down to personal preference. The problem with any of these best practices is that they change and they also are kind of subjective in a lot of ways. But specifically for myself, I almost always use Git right away. There's no reason really not to. If you're already making code changes, taking one extra step to say, Git init to create the initial repository, then Git add whenever you've made some changes, and then Git commit when you're comfortable with those changes getting actually snapshotted, saved off. That's all you have to do. So it's an extra, like, 2 seconds worth of effort, really. So I would suggest using it for everything and using it early because it's much harder to do it later on. Any of these things is much harder to do after you've already created a lot of the stuff. It's really great. Which was a point I meant to make, was start all this stuff as early as possible. And I think Bob also had a question, or did you? Yeah.
Just wanted to throw on a couple more suggestions on that. The beauty with Git, as you say, is it's very little effort to start with. You can start with Git and not set up all the GitHub machinery and pull requests and all of that. But if you start with just doing the Git repository, then when you decide you need more machinery later, it's really easy to transition.
Yeah.
So that's really important. Also want to throw in 2 more suggestions. On Git, there's this lovely little gamified thing called Oh My Git, which lets you visualize what's going on in the repository when you change stuff. So that's really fun. And one thing I threw in the Zoom chat in terms of keeping your documentation synced, there's the no longer new typing hints in Python, which doesn't get you the whole doc string, at least gets you a little of that information that's very tightly tied to the actual function definition.
Yeah, awesome. Thanks for those resources. Yeah, and one other really good resource is Atlassian. If you have anything Git oriented that you want to learn about, they have like all the information you'd ever need. And another way to visualize your Git repositories is Git Kraken. They're also really good. But yeah, all right. And I'm here again all week. So if you have any questions, feel free to stop by. I'll have some stickers for the USRSC and some for coffees, which I did not mention, but it's another NASA Drive Science Center working on heliophysics research. So, all right, thank you.
Just pin it on.
Yeah.
Here, 1 second.
This is easier to walk around questions.
Okay. Sure. Good to. Just pocket that. Cool. You guys can hear me okay? Sweet. All right, let me pull up my presentation. All right. What's that? Oh, stop sharing?
Oh, I see. Cool.
I know how to fix this now.
Okay.
This backwards is so. That should work.
Okay, sweet. Thanks, Julie. All right, so my name is Peter Shumate. I work at Johns Hopkins Applied Physics Lab. I'm here to talk about HelioCloud, which is a project I've been working on for a while. Here's all with Sarah Rourke. I think she might be in. Oh, yep, sweet. Yeah, she's here as well, supporting HelioCloud. And yeah, so I got to get into this. It's something that we've been working on to support doing software or research using the cloud. And I guess a good way to get into it is to think of HelioCloud provides a tool that brings researchers to computational resource and storage. So instead of using your laptop or your own machinery, if you don't have access to a high-performance computing cluster, and maybe you thought about using the cloud, HelioCloud is an option for that. We provide the infrastructure interface to get you onto these computing clusters. So yeah, the science problem is that the research can come at a high computational cost. Why not make use of the cloud? You just have to pay for it. But the hurdle is that getting into the cloud and learning about the cloud has a substantial learning curve. Like if you can see that diagram there, if you've seen that before, when you start to design cloud resources, it can get really complicated and you can make an entire career and life out of it, to be honest. So like if you have a lot of grant money and you want to start using that on cloud, you're going to come out of it a cloud developer and not have some paper to publish. So that's where HelioCloud comes in. We provide that infrastructure. We have 3 core capabilities. We provide Task Hub, which is a Jupyter Hub interface. If you're familiar with Jupyter notebooks, you can write Python in like a web interface. We provide that built on top of cloud resources, so you can distribute your scripts on multiple different compute clusters using a tool called Kubernetes. We also provide a dashboard if you actually want to get more into the weeds with AWS resources. You can actually spin up your own VMs and connect to them directly, as well as a registry where you can index your data. Like if your institute has a massive data set that you want to make readily available on the cloud, we can work with you or you work with us to index it and make it readily available using cloud resources. So yeah, I have a slide on architecture. I don't have to get into this too much because it really gets into the weeds. If you are really curious about what HelioCloud looks like under the hood, I'd be more than happy to talk about it, but that's I guess not as applicable for this. Okay, cool. So I really want to spend a lot of time getting everybody set up because HelioCloud is the tool that this whole week is going to be based on. All of these science notebooks are going to be running on HelioCloud. And so I want to get everybody set up right now. And I imagine nobody has created an account yet. Nobody's gotten signed up. So yeah, if you can go ahead and navigate to the link there, maybe send it out in Slack as well. Cool. So yeah, when you log in, or when you hit that website, you should see this web page. Need you to go ahead and sign up. Use any email that you can access here because you'll need to enter an MFA token. And that should honestly take a minute or two once everybody gets signed up. Sorry? Oh, sure. Yeah, let me know if anybody has any questions or any issues when logging in. Oh, yep. Yeah, just let me know. Yeah, if anybody's having any issues, raise your hand. Come by and help you out. Um, Let me take a look at
No, I know it's not.
Let me see daily. Well, it might be like an AWS thing under the hood. Shoot. Sarah, would you be able to? Okay, cool. Yeah, we're taking a look at that right now. Is anybody else getting that issue as well? Okay.
How's the chat, Sean? Are people doing okay in there?
Okay, interesting. Was anybody able to get through though? Okay, cool. Hmm.
Email that she has a Slack link and post a bunch of links with that URL. But I think it's slightly differently.
Okay. You seen anywhere? Yep.
Just to be clear for everyone on Zoom, we are working on the exceeded daily email limit message that everyone is getting. Apologies and stand by.
Yeah, it seems like there was like a 14 emails per second limit on AWS, so maybe we might hit that. We're looking into it. What is it?
Well, actually, while you guys are waiting, my presentation is next, and the first thing I was gonna have you do is ask you to work in groups. And I think based on the number of people that were able to log in, I think if you form groups, everybody will be able to, have access to the community cloud. So, if you're logged in already, say hello to your neighbor. And, you're probably gonna learn more from your neighbors than me today. And, we will work out these issues in the next few minutes.
So yeah, in the meantime then, whoever has gotten in, let's go ahead and get you set up with the science notebooks. So if you signed in, you should see like a page to spin up a server. You can go ahead and spin up that server. And we'll get you to the actual Jupyter Hub interface. Yeah, sure. Oh, sweet. Yeah, I've seen all the users logging in. Nice.
Is the Git link in the Slack and?
Sure. So if we can go ahead and send that in Slack as well. Yes. Cool. Thank you. Yep. The cloud is great. Sometimes you get rate limited, but when it works, it's great. Cool. Yeah, so a get URL should have been sent out in Slack. If you can enter that once you get the server spun up, you should see a Jupyter Hub interface, and the top left, like a blue button with a plus on it. A couple over, you'll see a git clone button, a funny little symbol. If you select that, paste in the URL, hit clone, that'll pull in the folder with all of the science notebooks.
The GitHub link is now in the general Slack. I just edited the message where I put the HelioCloud link originally. So look at that.
There's not a daily one yet.
No, I can't even. So it doesn't.
It's not a lot of emails either. Oh. It's incognito. Oh, just cognito. Cool. People have successfully cloned the repo. Nice. Is anybody still getting the email issue if they've tried again? Okay, cool. Have you been like repeatedly trying or? Okay. All right. Yeah, we're checking that out still. We'll get you in.
I'm here. What else do you have to cover?
This was it for me. Getting the notebook set up, and for anybody that wasn't able to get the email, I will try to go around and grab your. I can set up a username for you and create an account manually if this persists, and we'll get you guys in.
Okay.
Cool. Other than that, I guess I'll pass it off.
Oh,
I think you're technically 10:05.
Oh, I didn't want to. Sorry. Oh, you're fine.
Okay. Well, I've this was the last for me. But yeah, if anybody has any questions throughout the day, if anything pops up, definitely reach out to any of the PyHC folks, myself or Sarah, and we'll be happy to help you guys out, troubleshoot any issues.
And all of these links so far have been copied and pasted over into the Slack. So if you're not on the Slack, get on the Slack.
Cool.
And I also linked Peter's slides, so you can go and see all this in one spot again too.
Cool, sweet. All right, thanks.
Okay, I'm going to take a few minutes to get set up, and I'm serious about working with people. We looked at the demographics from the survey of people here. We have people that are very new and people that are very experienced. And as I said earlier, I think in sessions like this, sometimes you learn more from your peers and from the people next to you with new ideas than you do from the instructor. And in fact, I did a presentation similar to this last time, and I have some new ideas for the solutions that were based on looking over students' shoulders. And so I think there's some real value to that. And I'd like you to say hello to your neighbor while I get set up and find HelioCloud. Try to find the Git repository.
Yeah.
Thank you. Where can I find the, Julie? I need to, oh, here it is. Hmm. Hmm.
I know there's
I'll give them a few minutes to introduce themselves. Did you have something to say?
Say.
Pardon me?
Good.
oh my God.
What you see on Zoom? Oh, wait, I got it here. I just want to see. Why isn't my screen showing? Julie? I don't know why my screen's not showing.
Maybe stop share for a second.
Oh, the whole window desktop.
Oh, yeah, it was probably shared. Okay.
Okay, let's get started. All right, looks like everybody's gotten to know at least one other person. And the first thing I'd like you to do is note that you should have in your directory these items. So science tutorials, scratch space, and then summer school 24 is what you just cloned. Yes, anybody know? Okay. And the first thing you're going to do with any Git repository, just as a good practice, especially if you're working on your own repository, sometimes I use code, or I develop code on 3 or 4 different computers. And if I don't do this, I run into problems. And so the first thing you do is cd to the directory, and I do a git pull. And what that does is we'll fetch everything from the remote repository on GitHub and download it. Now, the other piece you have to remember is when you're done working for the day is to do a git push. Now, those 2 things you're going to remind yourself over and over to do, and you're going to make that mistake for the rest of your career if you're like me. All right, and so I did that by opening a terminal. It's not necessary now because of the fact that you have a fresh repository. And I'll also mention, as a follow-up to Alex's presentation, where he was talking about code development, and one of the questions was how do you structure a repository if you're just starting out? I'm going to cover that a lot bit on Wednesday. And so that's something be discussed in this how-to session. All right, so for today's activity, let me pull up this introduction. Maybe too big. Oh boy. So today we're talking primarily about different PyHC packages, PyHC core packages. And one of the packages that I'm involved in is called Happy Client. And it's a package that allows you to obtain time series-like data from 9, actually more now, data servers with a few lines of code. And then on top of it, there's another package called Happy Plot, which will plot data obtained from a Happy server. And so this is one of the ways that you can get data from Heliophysics type data is through this Happy client, and I'll give more details on that shortly. And today and tomorrow, you'll also learn of other different packages that'll allow you to obtain Heliophysics data. And some of the other package actually interface with this Happy client. And so you'll have access to all of Happy data if you use something like Komodo, for example. And I think PySpeedas also has an interface to the Happy data. And so it's the Heliophysics Application Programmers Interface. It's essentially an API for data, for time series-like data. And the reason I got involved in this is, as a scientist in my early days, I got really good at dealing with file formats, CDF, HDF, and then arbitrary ASCII formats and learning how to parse that. And that always takes a lot of time, compare it, the amount of time to write a paper versus the amount of time to get the data you need for it. It takes a very long time. And so we got together with some software developers and some people that develop code for and data for instruments. And we said, what we really need to do is come up with a single interface that you can access data, a common interface of accessing data through an API, so that you just need a single client, and that client can work in different languages. And so you can actually access Happy data through Python, which is the only thing I'm going to cover today, but also MATLAB, JavaScript, Java, with just a few lines of code. And again, the objective was just to make it easier for the scientists to get the data and move on with their lives and start doing the analysis. The place I always recommend as a starting point is this web page, which is linked to, and it has a list of the available Happy servers that you can pick from this drop-down list. And you do a selection here, and then it gives you a list of data sets and so on. And actually, just let me follow through on this. I'm going to just show you how this interface works. You can return data, image, or a script. The image option allows you to automatically generate code for these different languages. And so you can see there's a couple of other PyHC packages in there that it'll auto-generate code for. And you can even do it from the command line with curl and get, wget. And so essentially you can just copy and paste the script and paste it into MATLAB. I don't know why I chose MATLAB given what we're doing today. Copy and paste the script and away you go with your data. Yeah, and so the motivation was, as I mentioned, is that a lot of different data providers will provide like a Python package or maybe a MATLAB package for accessing their data. And we said, really need to standardize that and make it just a single API, just sort of like CDF files or HDF files are kind of a standard for data access. We wanted a standard for API access. And somebody had a question? No? Yeah. The happy, yes, thank you. What happened here? Yes, so the question was, is there a delay between when the data is available through Happy and when it's available just from the data provider? And as far as I know, all of the data that's available from the data provider by other means, by like files or so on, should be available through the Happy interface because they essentially took their data system and bolted on top of it this API. Now there is a case like intermagnet data where some of their data sets are embargoed, so nobody can access it through any API for a few days for certain ground magnetometer stations. But yeah, I think it should be all available. And if it isn't, I'd like to know about it. We'll talk to them. Okay, so the Happy Python software is a big part of this was development of the API standard. I won't give too many details on that. And then also development of software that implements a standard. And so we wanted the API to be simple enough that it was easy to build a client piece of software that ingests the data, but the API had to be rich enough such that complicated data sets could be ingested. One thing I want to note about finding data, there'll be a talk on Friday about doing search for data in the heliophysics community. I think most of us have had the experience, we Google for data, or quite often we talk to another scientist or advisor tells us what data set we need to look for and where to get it. There are a couple of efforts where they're trying to improve that. So you can do, for example, a faceted search. You can say, I want satellite data that's magnetometer data and it's in a certain region. I'm not going to talk about that today, but I'll just point to some general resources that I use for finding data. One is the Heliophysics data portal, which allows you to do some of that faceted search. And when you do the search, you'll get links that say, access this through, you can get the files or access it through Happy, for example. And then for all things Happy, I just go to this web page here, where it just has an up-to-date list of everything that's available. And right, so today I'm going to cover two notebooks. One is the very basics. And so the HelioCloud has already installed the Happy client and Happy plot. And I'm going to do some setup here. Usually set the images to be SVG instead of PNG so they're not blurry. And then the first thing I'm going to do is just do a help on the Happy client. The general syntax is as follows. I can't make this screen bigger and it renders kind of funny on here. You pass it a server data set parameters, start and stop. And it's somewhat similar to this interface here. So if I do an example query, we kind of followed the interface of that you see here. If you form a URL to a Happy data set, question mark data set is equal to this, and so on. And this essentially translates to a call in Python. And the output format or the streaming format of the Happy client by default is ASCII, but there's also a very fast binary format that the clients use. And so that is the interface, and I'll just give an example of its use here. And I'll also mention that there is another important function that you'll need to use called happy time to date time. And so essentially the happy standard says all times are going to be a ISO string like 2001-0101 T and then a time. And this thing will translate that string to a Python date time, which you'll need for various things, for example, plotting with matplotlib. And then finally, I'll do a help on happy plot. And essentially the call is fairly simple, but I'm going to demonstrate it here. So the first thing I'm going to do is explain this. We're going to obtain OmniWeb data. Probably the most common data set that people look at is the DST index. And in CETA-Web, for example, for some reason, it's called DST 1800. I used to know why that was, but it was 10 years ago. But this is how you get it. You essentially say, this is my happy server. It's a direct link to the CETA-Web. This is the data set. And again, if you want to find the data set, I'll find this over here. Somebody have a question? No? You can do a search on the data set here. And I think it was, what was it? Omni 2, I can do a search on. And then you can see additional information about this data set. Starts time is stop time. They're always in this format. And the parameters you specify by a comma separated list. And so here I'm going to select 2 parameters from that data set. And so here's the full list of parameters that you can pick. In the Python client, if you just say parameters is equal to an empty string, it'll give you all parameters. I discourage you guys from changing this too much because we have the data cached locally. The happy client, what it does is when you first make a request, it stores the data locally if you have caching turned on. So if you rerun the code, it says I have the data and I'm not going to re-get it, refetch it. And so we've done that here for the summer school because with so many people, we're likely to break things. All right, so here I'm going to turn on logging, so it tells me what to do. And then I have this cache directory. Don't change any of that. And so here it's got the data, and then I'm going to inspect the metadata. The metadata comes in the form of a Python dictionary, and you'll note that the Python dictionary will look very much like the metadata that you would get on the web page. So the native metadata format for happy is JSON. And so this is just a one-to-one mapping of that JSON to a Python dict. And let me close this. And then now that we have the data, we're just going to plot it. And here you go. So this is using the happy plot client. You pass it the data and you pass it the metadata. Let me have a look at that data object. We looked at the metadata object. So I'm going to look at data. Oops. And essentially it's a NumPy array with named fields. Have people used that before? People have used NumPy arrays, but have you used NumPy arrays with named fields? Okay. Essentially, it allows you to have one big array with different columns or different parts of the array that have different data types. So I think here you have a byte array for the time, and then you have integer for DST index, and then the other parameter is a float. And if you look at the very bottom, it says the data type for time is a string with 24 characters, DST is an integer, and then the proton data is a float. And so the one thing to keep in mind actually is that the first parameter that you'll always get from the happy data set is always going to be the primary time index. However, different data providers name that thing differently sometimes. So here, the data provider has called it time. Sometimes you might see epoch, sometimes you might see epoch lowercase, uppercase, and so on. And so you usually have to look for that to find it. And I'll show you other ways of doing that automatically so you don't have to think about it. And so here's the general way of cracking open that data set. I'm going to press enter. the time array is a Python byte array, a byte literal array. And so I'm looking at those here. And to convert it to a time array or to date times, you call happy time to date time. And then here I'm extracting the DST index, and I'm not sure why I called it that variable. That's kind of an odd choice, but away we go. All right, so as a second example, I'm going to look at data from the Discover spacecraft. What's the Discover spacecraft? Who knows? Somebody must know. Yeah. At L1, yeah. So it's one of previously it was an ACE spacecraft, but we have usually have a spacecraft at the so-called L1 Lagrangian point. That's about 50 minutes upstream, and we used to have the ACE satellite, and we also used to now we have the Discover satellite, and that's used for a lot of space weather prediction. All right, so I am going to choose this and just do a full run. And it's reading that data set and should be plotting it. One of the things I'm going to tell you as best practices on Wednesday is that when you write code, you should, whenever you're going to do an operation that might take a little bit of time, you should always put, I'm about to do this, I did this. And it looks like I halfway did it. So here I said, I'm reading the data, I'm reading this data set, this is the metadata set, and this is the data. But then I didn't have something that said, I'm plotting this data, I'm done plotting this data. And I regret not doing that for the reason that's become obvious, because I was stuck here wondering what was going on. Okay, so here's the data set, and that's the basic usage. All right, and then one other comment, we do have this somewhat of a strange way of doing things. In Python, it might seem kind of weird to have to specify parameters as a comma-separated list. You might want to have that as like a dictionary or an array of strings. We chose to do this just because we do it the same way for all clients. And so it's probably not the way you would want to do it in Python, but just for consistency with the web API and the MATLAB and R and all the other languages that we support, we did it this way. So I guess that's somewhat of an apology. All right, so the parameter order is important. And so here we have the order transposed, and I'm going to untranspose those. And away we go. Not sure what that error is. GSE position. It's not in meta. I have a feeling I didn't execute something upstairs here. Yes, thank you. Yes, this always gets me. This is why I don't like notebooks. So thank you. Yeah, you have to run where is discover because I've set this data set and parameters. Thank you. And so this immediately brings back a plot of these two things of the moon. And then now if I run this, let me, now it should work. Reading the data set, and then it's going to plot. No. And this is, oh yeah, does happy plot take the same arguments as matplotlib? And the answer is no. And I think as I was working with this and preparing this, I think this is a flaw. Let me just show you. Happy plot takes the output of happy, right? And on the back end, happy plot is essentially reading the metadata and making labels and then calling matplotlib. Now the problem is that there's not an easy way to access all of the logic that was going on behind the scenes to create these labels. And so ideally, this thing would have an option, or there would be a function that would dump out that metadata or just say label the plots appropriately, and then I'm going to fill in with my own data. And that's something that I think should exist. And so I think it's a flaw in what I've done here. And in the PyHC community, I've used a lot of plotting software. And what I found is many people do it like this, where I look at it and I say, wow, they produce some really pretty plots, but now I got to figure out how to create their data structures. And that's just something that exists. And I'll probably give a talk about that at some point because it's a mistake I made. And as a user, not something that's fun. Okay, so we have about 5 minutes before the break, and we have a question. Oh, yeah, so the error that I had was because as you do these notebooks, you have to do them, you have to execute each shell or each part. So here, if you execute this, then I think this server and data set are defined. And then this cell assumed that server and data set were pointing to the correct thing. And so what I had done was I skipped that cell, and so it was using the wrong server. And that server was saying, hey, I don't have that data set. All right, and so doing this backwards. So the question was, what did I do to fix the error that I just had? And the answer is just run all the code in the right order. So Julie, just point at me when somebody asks a question, and then I'll remember to repeat it with the microphone, or we'll just start throwing microphones. Yes, other questions? Okay, so we have about 5 minutes before the break, and I would like you guys to try and break things. Excuse me. I have 2 problems that I'd like you to start on. And the first problem should be straightforward. It's kind of a one-off based on everything you saw above. And then the second one is not so obvious. It might take a little bit of thought. And so I'm going to just allow you guys to have some time to work on this. And then I and hopefully other instructors will circulate and try to help answer questions. And I will call a break in 5 minutes. Is that right, Julie? I'll call break in 5 minutes. And then after the break, I'll give you a little more time to work, and then I'll start going through the solutions. And then the second notebook, if you're very good, feel free to burn through the other notebook, try all the problems. But I've essentially introduced you to everything you need to know about Happy. Everything else is kind of Python and fighting with that. Okay, so work for 5 minutes and away we go. I'm going to take off my microphone or turn it off.
Okay. We officially are on a break for the next 30 minutes. If you want to get up, get water, stretch your legs, that kind of thing, or you can keep working. Up to you. Okay, everyone, we're going to start up again. Before Bob gets back into it, just quick comments. If you have a question, make sure to raise your hand, and myself or Alex have mics, and we'll run around and get your questions for you, just so that people online can hear and benefit from them too. Also, if you go out this door, like in this little alcove right here against the wall, I have the signups for escape room, axe throwing Wednesday night, if you're interested in that. Also, all the stickers for the various projects and things, you know, propaganda will be out there for you to grab and for you to take.
Okay, should be back on. Can I get a thumbs up from Zoom? Make sure that you guys can hear me. And I need to find out where I am. You did? Somebody gave me a thumbs up? Okay. Okay. Okay, just let me get set up here, figure out where this problem was. Okay, so most of you guys had a chance to work on that first problem, and I think everybody got to where I wanted them to get to. And a few of the things you needed to know is how to use that website to find the variable names. You should have realized that it's not always obvious what variable or what parameter you need. You have to poke around. And to that I say, welcome to Heliophysics. We made it really easy to access the data if you know what you're looking for. You can just use that menu and grab it. If you don't, you're on, you know, I gave you some links as to searching for data, and there are some tools out there to make it a little bit easier, but that's a subject of a different talk. I think people are familiar now with the happy data structure. The metadata is a dictionary. The thing that comes out of happy client is data as a NumPy array with named fields. And then happy plot will allow you to pass it data and metadata, and it'll just create a plot. And a lot of people asked, and I asked this too, even though I participated in the creation of this, is how do you combine data to plot from two different servers? There's not an easy way to do that. But I'm going to tell you what I usually do anyway. Is almost nobody wants to use somebody else's plotting code. There's a lot of really good plotting code out there. But what I find is I try not to make things too sophisticated or too perfect, because you give it to somebody and they say, well, I want to do this one little thing. And you think, well, that we can't quite do that easily. We have to contort ourselves. And so what I always look for in Python packages, so for you who are eventually going to make a Python package or tool, is I always want to get to the nut. So if you give me a data array, I want to unpack that into something I know about, like a NumPy array, and I want to do it myself. And that's what I'm going to show you how to do now, because I'm assuming probably half of you are of that opinion. And so there were some hints to how to do that earlier, and a lot of people asked me about this. Oh, and then some people asked me the question about why did I get data from two different data servers? And just as best practices, when I do problems, I always solve problems two different ways to check my answer. When I look at data, I always want to look at data from two different sources. If there was only data from one source here, I would have done a Google image search to make sure and looked at what the plot that was coming out of the data server was consistent with what's on the images. And so that was the point of doing this exercise. And the other point is that if you look at the numbers, you'll notice that the position of the spacecraft isn't quite exactly the same from those two different data providers. And so yet another reason from doing it from two different data providers is it gives you a little bit of an uncertainty that you have to account for, because each data provider might do their calculation in a slightly different way. All right, and so just to give you a solution, and I'll post the solutions here in a second. Well, I'll show you the solutions, and then I'll also post them. And before I get to the matplotlib, I want to talk about something that came up quite often. some people were mixing up and looking for the data sets. They were trying to, copy and paste the data, the happy data URL. And in this URL, where is this? Why isn't the URL showing up in this window? You're using Safari. It's up here. It's kind of hard to see, but here you see this hash, and then server is equal to something, and so on. Now, if you have this URL, you can send it to somebody, and you can say, hey, look at this, and it's going to pull up the interface just like it was. But this isn't a URL to a happy server. The happy server is this thing, and that's whatever you enter as your server parameter, and that client always has to end in happy. And so that was a mistake a number of people made. And then the other thing was trying to figure out what to enter. So I was doing discover, DSC. And so here, discover pre or orbit pre. And again, you got to do a little bit of research to figure out what this stuff is. There was GSE underscore position. And what I typically do is you can choose to look at the data, to inspect the data. You can have it create a plot. And the actual thing that's rendering this is that Python code that you've been working with. But I also just have it automatically create a script. And so here we're just using plain Python. And then I just copy and paste this information as the information that you need. All right, so now on to cracking open the data. This thing was what was returned by a call to happy, data underscore CEDAWeb, meta underscore CEDAWeb. And then I could have inspected it. I just do data, enter. You can see it has two parameters, and I'm making the mistake as before that I'm not executing code in order. Sorry about that. Oh, this is the thing I want to look at. So GSE underscore position is just a plain old NumPy array. And then data underscore CEDAWeb is ND array with named fields. So it has that time, and then it has a vector here. So it's a 3 vector of the position. And so I pulled that out. So now I have some date times and GSE position, and then I can do a plot. And I should mention on the README for the happy client, there's a whole bunch of examples. For example, if you use ND cubes, there's an example of taking that data structure and dumping it into an ND cube, also a pandas data frame, and some other things. And actually, we're going to get to that a little bit. I'll have you solve some problems. All right. Are there questions? No? I just want to go through the solution to this second problem here. How many people have used the DST index, have plotted it? Oh, what is a DST index for somebody who knows? Pardon me? Ground magnetometer, right? All right, Mr. ChatGPT. Or no, Mr. Link, you followed that link. Yeah, so essentially we have mid-latitude stations, Hermanus, Honolulu, and St. John's, and one other place at mid-latitudes. And they're measuring the magnetic field, the horizontal intensity of the magnetic field, which is typically constant and approximately dipolar. And essentially when you have currents in the upper atmosphere and magnetosphere, they modify that current. And so you'll have magnetometer values that are on the order of tens of thousands of nanoteslas, and then you'll get perturbations on the order of, say, 500 nanoteslas. They're very difficult to see. If you have a compass and you looked at it closely enough and your hand wasn't shaking, you might be able to see a little bit of a fluctuation. But this is an index that represents a measure of magnetospheric activity. It's a mid-latitude one, so it's mostly due to currents that are flowing in a ring around Earth, but I don't want to get distracted by the physics of this. I just want to talk about the data and assume that you're going to do the physics. So the example here is you're given these codes, and Intermagnet is a site that has a collection of a whole bunch of data. And so here I'm going to suppose I want to get some of that data, and I'm just going to search HER, Hermanus, and we can see there's a bunch of choices here. And as usual, as I said, get used to it. As usual, we have data set names, and there may or may not be some pretty good metadata that tells us what we want. I happen to know that we want the H component. And so here we have the adjusted minute data, 1 minute cadence data in HDZF. So H is the horizontal magnitude, D is the declination, so that is up, down. And then Z is the vertical field, and then F is the magnitude. So I hope I got that right. And so what I'm going to do is I want to look at data, and I'm going to look at field vector, field magnitude, and I'm going to look at the script, and I'll do Python. And so I have something here, and I'm going to kill off those times. Kill off some of this information here. Oops. And I'm going to copy some code from earlier. All right, so it should be loading the data. Yeah, and it's got it. And then again, it's just the usual thing. So data. Should have printed that out. Yeah. So the data is a NumPy dict. All right, so the point of that was that's a common thing you want to do is, you're looking at the DST index and somebody tells you it's based on these data, and ideally you have easy access to the data. And so the idea with happy is that it should be as simple as I just made it. And again, with the caveat that you know what you're looking for, away you go. And so I'll plot the solutions for this. But essentially, if you wanted to, you could take the data from those 4 different magnetometers, look at the description of the DST index, and try to recreate it, for example. And there's also other indices where they pull in more magnetometer data instead of just 4 magnetometers. Okay. Are there any questions? Any questions online? Yeah, no, yes, no? Somebody made a sound? No. Thumbs down. So for the rest of the time, you can look at this second notebook. And also that problem that I just started on, the second problem on the first notebook, and work through it. And I think at this point, it's mostly practice, and you guys know how to use the interface. And I think what will be useful for you guys is to get to explore the data. And what I'm going to do is stop you guys in, how much time do I have? 11:50. Okay, so I'm going to stop you guys at 11:40. And your task is either to work through those problems, ask questions, or do something interesting. You have access to all these data. Pull up a data set, an event, tell me what the squiggles mean. Do some sort of intercomparison based on your research. And ideally, I'll ask somebody to give a short presentation. Ideally, it's based on your research and something that shows the power of this. So go to work and again, feel free to ask questions. What was fun? Yeah, one thing to keep in mind here is in the code, it tells you the max and the min available data. But if you make that request, it's going to take a long time, and especially if you guys are all hitting somebody else's server. So I gave you some specific time ranges, and the reason was I had cached the data. It's okay if you could do other time ranges. I tried it just now and it works. But yeah, just be careful not to choose the maximum and minimum time range. Somebody was kind of anticipating the next the next example. They said, well, how do I figure out what data sets are available from the server? Was that kind of the question? Calling the parameters. Yeah, that's the way I have shown you how to do it was basically going to this web page. But I think what you're saying is, well, I kind of like to do that programmatically. I'm going to put words in your mouth, but so that's on the next activity. And you do something like this. I'll just do this will give you, yeah, a list of all of the data set IDs. And then once you know an ID, I can do server, and then I'm going to do this as the ID, and then it's going to tell me the parameters that are in there. So it's essentially drilling down like this. Yeah, 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 yeah. Exactly, yeah. And so I don't think anybody will get to it, but there's some advanced problems of saying, build a table of all the metadata that's available. Yeah, yes. Actually, let me show you the notebook that it's in. It is, yeah, it's, what section is that in? Metadata, section 6 of the second notebook. Covers some of that metadata automation. Um, This plus, if you go to the, if you do Happy Client, go to, let's see, or if you Google Happy Client GitHub. And then it's with a space before the G. Yeah. Yeah, Client Python. Now, if you scroll down, there's a little bit of a longer tutorial, but the best we have is actually the walkthrough that I'm doing here that kind of talks about the fundamentals, but it does assume that you've worked with NumPy and Matplotlib before. So it might not be might not be enough. You might want to look at some. Okay, are you on?
Yeah.
Okay, I'll introduce you. This is Bella, and she's going to present what she did and show us how she did it. And if you can share her screen.
Can you see my screen?
Yes.
Okay.
No wrong answers.
I didn't do anything fancy. I just I wanted to see if I could use this to find some data I always look at currently. Like the research I'm doing is a collisional analysis between like the solar wind when it goes to PSP and to solar orbiters. So I took one of my random dates and plugged in. I used CetaWeb. I used a data set I'm familiar with, grabbed some parameters, the dates I was interested in, and yeah, just plotted it the same way we've been doing everything. I didn't get the same luck though when I tried using PSP because the data set was empty. I don't know why, but this one just looks empty. And that's all I did. Nothing crazy.
Hey. All right, well, thank you for that contribution. I want to make a few comments about her experience and just a general experience. And I'm going to, I guess Alex talked about this a little bit, and I'm going to reinforce it on Wednesday. You guys are using Python code written by PyHC developers, and you're using data from data providers. And one thing I always tell people, you know the expression, if you see something, say something? Yeah? All right. Well, everybody operates kind of like, don't be a snitch, right? If something goes wrong, you don't report it. But, you know, to be part of a community, if there's a software error or a data error, you really need to provide feedback. And, you know, on a lot of these data providers and also on the web pages for the code, there's places where you can report issues, and I'll show you how to do that actually on Wednesday. And there's also data providers. So if something goes wrong and you're pretty sure it's wrong, tell them. You know, you think, well, it's going to take you time, but invariably what I find is I'll tell somebody something went wrong, and then I'll work on some other project, and I'll come back to the project and think, oh, it was broken, but then they fixed it because I said something. And I think I really want to reinforce that kind of behavior. And so she encountered some issues. Those are, you don't have to report those because those are known issues.
Okay.
The CetaWeb data server is undergoing an overhaul. And if you show me your plot here.
Which one, the PSP or
the
solar
PSP
order?
slot, yeah. The one where it just said column 0, column 1, column 2.
Here.
The one with the nice squigglies, yeah. Very
Which
scientific
one?
term.
I don't know. Oh, that was solar orbiter.
Oh, I'm sorry, yeah, solar orbiter.
Okay.
Thank you, yeah. So you can see the happy server isn't providing individual column labels, and so the CetaWeb people, based on feedback and sort of my demands, in part, said, you know, you got to provide better metadata. And the idea with happy metadata is, I've always said, you got to provide enough metadata so that software can automatically create a plot that's scientifically meaningful, that could almost be have enough information that you could put it in the scientific journal. Clearly, they're not meeting that mark there, and we're trying to push these people along, and your feedback always helps continue with that. That's the second to last thing I wanted to say. And the final thing is, Julie is going to send a feedback form out at the very end of the week. This is the second time I've done a presentation on this, and I usually don't get it right till the third time. My takeaways here are, I think people got out of this what I wanted them to do, which is essentially how to generally do things. And there were a lot of stumbles along the way, and some of those are avoidable, but many of them aren't. But the one thing is, I think there maybe about 25% of you didn't have the experience with the Python syntax. And so I sort of started with assuming that you've dealt with NumPy's arrays and subsetted those. And so we need ideas or just different ways of thinking about having you work on problems so that you kind of meet the prerequisites for doing some of these things. And so again, she'll send out that form on Friday, and your feedback is most welcome. Over to Julie.
Thank you. Thanks, Bob. All right, next up, we're going to move on from happy to a little bit of an AstroPy diversion. And I think, is it Will or Nabil who's doing that? All right, Nabil. And that's gonna take us until 12:35 and then lunch will be after that. Check social. Sean put an
We
idea
have
for lunch in the
one
social.
question.
Go ahead.
Oh, sorry. One quick question was, so the other notebooks that we have, can we just do it on our own time? And if you have questions, come back to like some other designated time, or in general, catch you?
So the question was if you had questions about different notebooks, what I recommend is you go to the Slack channel and there is different subsections for the different packages. Post your questions there and we'll answer them when we answer them. You know, we'll look at them periodically throughout the day. And so that, yeah, that'd be great if people are continuing to work. Paying attention. Hello? Okay, testing. Yeah. I'm just gonna zip this. Yeah. Well, good morning, everyone. So I'm Nabil Frage. I'm a research software engineer at Lockheed Martin Space and Astrophysical Laboratory in sunny Palo Alto. My friend and colleague, Will Barnes, is a NASA Goddard and American University. He is the deputy lead developer of SunPy, and between the two of us, we'll be presenting a introduction to SunPy and AstroPy, but I will caveat the AstroPy is being taught through the lens of SunPy. So I'm going to start off by. So I just want to thank a bunch of people. I want to thank a bunch of people who made obviously this material possible. Unfortunately, they couldn't be here today. Albert Shee, Laura Hayes, David Stansby, Stuart Mufford, Halim. So there's a lot of AstroPy people that contribute to this. Eric Tollard and a few others. So I want to just start off by describing SunPy. So there's technically two spellings. There's the capital S and capital P SunPy, and then there is the lowercase ones. So SunPy is a Python library. We call it the core package of the SunPy project, and it is designed to be a community-developed, free and open source software package. Whereas the SunPy project was established to oversee the development of the library, but also to hopefully establish a community of users, programmers, maintainers, people who have named roles within the project itself, but also to expand upon the core library. So while the core library provides functionality, the idea is that it was supposed to be a foundation where some of the more analysis tools or the more kind of experimental code will be living in what is called affiliate packages. And obviously we do tutorials, workshops, we have community meetings in person every year. And obviously AstroPy itself follows a very similar method. We based ourselves primarily on AstroPy. Well, AstroPy is again a community-driven, open source, open development Python library for astronomy. And again, the project was established to manage not only the core library, but also the growing number of packages that orbit around AstroPy. So in this tutorial, we're going to be covering a flare and a CME that happened a couple of years ago, seen through the lens of the Solar Dynamics Observatory, AA, atmospheric imaging assembly, stereo, and GOES. And so here is just a HelioViewer. If you ever need to like browse solar heliophysics data quickly, helioviewer.org allows you to make movies, go through a range of image data, and output nice movies for you if you want. So in modern solar physics, what is I think termed the multi-messenger phase of solar physics is that back when I started, I was a ground-based observer. I went to a telescope, I took some data. Now these days, that's not what you do. Well, you do that, but you also
add extra data sets from space-based missions. Obviously, Solar Orbiter and Parker Solar Probe are the two kind of more famous missions currently. Obviously, SDO has been up for at least, I think, 10 years now. But due to the fact that these missions move around the sun, it is very important to know exactly where these satellites are. And one of the tools to do this is a solar map even. I don't know why I spoke like I was German, apologies. So obviously this will be covered slightly on the the Thursday tutorial that Will be giving, where he'll be covering more instruments than I am. But this tool allows you just to map out in a nice, simple way where everything is at a specific time. So we're going to be covering data search, data download, the two main data containers within SunPy, and working with some solar coordinates. So as I was saying, we cover AstroPy through the SunPy lens. The 2022 summer school material is available for AstroPy. It is about 9 hours of material covering everything in AstroPy. Don't worry, we're not covering that today. But if you do want to have a look at it, it's available right there. We have a couple of exercises, so there'll be nice little orange boxes like that. And I just wanted to echo Bob's message. We aim to be community developed. So, and that needs people to give us feedback. If something breaks, you don't understand something, we try to have extensive documentation. I'm going to open this right now. Well, sorry, I'm going to blind everyone. We have several chat platforms. So we have our Slack alternative element. We also have an open astronomy discourse where you can ask SunPy questions, but also with AstroPy and other libraries. So if obviously, and you have a GitHub account, you can just open an issue on our repository. Please don't feel embarrassed or have any hesitations, because we want people to report issues, of whether it be problems or things you don't understand. Please just get in touch. And here are some AstroPy. AstroPy also has the same structure, except they use Slack. So let's see if this works. So to start off with, we're going to be downloading some data, and obviously we're going to probably make someone very angry once we all download about 100 megabytes of data from. So if the data does break, you can uncomment out the last line, and that is being cached on HelioCloud. So if the data does fail to download, you can just uncomment this out. Everything else will carry on as running as is. Right. So again, just to summarize what we'll be covering. Oh, just a reminder, if you have questions, just put your hand up. Hopefully someone with a microphone will come around and you can just interrupt, it's not a problem. Or Slack, yep, apologies, Slack as well. So we're going to cover AstroPy units. We're going to cover AstroPy time. We're going to search for data through SunPy. We're then going to stop there for lunch. And then after lunch, we're going to open this data. We're going to visualize this data. We're going to play with some coordinates. And then we're going to do some quick time series analysis at the end. So I'm going to start with units. So for, I guess, the older generation, I include myself included, in the days of Fortran and C, if you had units, you had values, you want to do calculations, you would typically either add a comment explaining what the value of the unit is, or you would just add it to the name of the variable. And if for the keynote, you probably have noticed the last line is wrong deliberately. Well, actually, I made this mistake without realizing when I typed this, but just goes to show that this method of units can lead to problems even in Python code. So that is not, doesn't matter the language. Unit frameworks have sprung up around a bunch of other languages to avoid this problem. And obviously the most famous one is the Mars Climate Orbiter, which I think failed to convert between meters and centimeters and inches and crashed into Mars due to it. So very important to think about units at the very start. So I'm going to be covering a subset of AstroPy units. The documentation is extensive. And there's going to be a few, I've put a few comments. So this cell for, so within certain Python libraries, there is a style choice about how you import certain things. So obviously, if you import NumPy, you typically do import NumPy as NP. AstroPy units tries to suggest that if you're going to use units, you should do import AstroPy.units as you. Obviously, it's Python, you can import it however you want, but that's how you're going to see it throughout this notebook. So obviously, a unit package needs to have units. So we're going to start off with a meter. And so AstroPy has tried to make sure that units like print nicely out into terminals. So as you can see, you have a nice LaTeX unit. Using the power of the Jupyter Notebook, you can add this help information, which tells you the docstring of the unit. But what underneath is happening is that AstroPy is assigning a physical type to all these units. So obviously, for meter, it's a length. This is how AstroPy underneath validates the calculations. And I would say there's probably at least 3 ways to define a unit in AstroPy units. So obviously, we've gone between M and meter. I'll do this. So we have a unit. What should we do with it? Well, we can tell it by a number. We now have 100 meters. We can create a list of units. And our favorite is we can take a meter and turn it into everyone's favorite wavelength unit, angstroms. So, okay, good start. Let's add some units then. Let's do some arithmetic. We can add them. Beautiful. I have 11 meters now. What happens if I add 1 meter to a gram? We get this very large error. Very large. You scroll all the way down, all the way down. Man, this keeps going. And you get the somewhat helpful, can only apply add function to quantities with compatible dimensions. And so on the surface level, AstroPy units ensures that if you are calculating anything, the units will match by the end. In addition, no, that did not do what I thought that would do. There are constants. And so we get to our first. No, whoops, wrong one. Scroll up. Our first example. I want a couple of minutes to see if you can work out the Schwarzschild black hole radius of the sun. I will clarify that I have been slightly mean here. There is one more constant that I have not imported. And this brings me to what you could consider the downside or the upside of Python. If I type this right, beautiful. When you're programming Python code and you're unfamiliar with the libraries, documentation is your first port of call. And AstroPy have a fairly extensive documentation structure that they overhauled recently. And they have this very large units subsection, which just keeps on going. And in this page, they define all of the constants, all of the units, so you can search and find the value that is missing to complete this equation. I'll give you 3 minutes.
If people are following along on the HelioCloud Git, the one that you want to open is not the instructional one,
yes,
part
yeah.
1 SunPy,
Sorry,
so that you don't see the answer right away.
No, apologies. I should have started there. Thank you, Alex. Yeah, I think it's actually the first one on the list is the problem. Yeah, so it's. Yeah, sorry, it's the second one. It's the second part 1, not the first one. I'll give it one more minute. Okay, and so I'm just going to run this. So the missing thing was the fact that AstroPy defines the solar mass, the solar radius, and the solar luminance within its units package. And so you actually have two choices here. You can actually do the import through the AstroPy units namespace, or you can actually just do, let's see if this is right. Nope. I cannot remember. You would think I would remember this exactly what I saw. Oh, right, it's not alias through. And you can do this instead. And there we are. And obviously, just to get something that's more, you can change this to kilometers, and it's just under 3 kilometers. Always a great undergraduate question to ask a physicist. So, in addition to this, units can be changed, transformed. And obviously, if you think about light, you can transform wavelengths into frequency. But by default, AstroPy gives you this very nasty error if you want to turn this into hertz. And it says they're not convertible, but obviously what you have to do, so AstroPy and SunPy try to avoid making assumptions for you. So these types of conversions, you have to explicitly opt in. And so this is why this errors. And so you have to use the spectral class. And we can then now convert between nanometers and hertz. In addition, they play nicely with NumPy. So we're going to import NumPy, and we're just going to work out the 90 degrees and 30 rads. And so the reason I bring this up first, because units are useful, but primarily the decision within SunPy was made that any place that requires a unit would be enforced. So, and this is where we get to downloading data. So part 1, data search and download with Fido. We called our download of Fido. I don't remember the history, but it exists now. And so the idea was that we would abstract away as much as we can from the search and downloading of data. The idea was, as a solar physicist, you don't care where the data comes from, you care that you have the correct data from an instrument, and it's been downloaded onto your machine. I will just highlight the extendable way. So on Wednesday, oh sorry, I keep saying Wednesday, on Thursday, we will show how to access solar orbiter data through the SOAR archive. But out of the box, the Fido essentially uses the Virtual Solar Observatory, the Joint Science Operations Center, a bunch of individual providers that we've written clients for, and some metadata only servers like the Heliophysics Events Knowledge Base. And as I said, others through a plugin system. So for example, you can use dkist. If you install the dkist Python tools, you can now search for dkist data and then download some of the dkist data through Fido. You have to install Globus and that'll pop up, but in theory, it all works. So the problem is that we have had a problem with discoverability within our documentation. And so the decision was also to go, okay, what happens if we print the client? If we print Fido, what should happen? And so we decided that it would then tell you this very large, it tell you as much information as it can through the representation. So it tells you all of the clients that are activated by default. So CD Web, Eve, you want to download Suvi data, Gong data, Lyra data. Just keeps going. Our main client obviously is the Virtual Solar Observatory. It provides access to a lot of solar physics data, and they are slowly expanding it with time. And so we can then search through any of these clients. You don't have to know what the clients are or what they're called. We provide an interface for you to search. And so this is done through what we call attributes. So when we did the FIDO import, we did act as a. So that's also something that we define as a style within our documentation for SunPy. The main ones we're going to be working on with is time, wavelength, and instrument. So this CME happened 2 years ago. I don't remember the exact time, so I left them here. So our first thing is most of our clients enforce a time, you require a time string. It's not true for every client, but most of them enforce a time. So we're starting there. So we're going to create our first time attribute. And I'm asking, and so what seems like a silly question is, what is this time object? So we can print it out, and we see the sunpy.net.address.time, and like, okay, sure, but why would you tell me this? So what we can do is we can do the .start of this time range, and this is where our first aside comes. Underneath, this is an AstroPy time. We convert all date time strings, all representation of time into an AstroPy time. And this is where we get our first aside. So I just want to preface this as to why AstroPy time exists, because obviously date times exist within the Python standard library. So for example, we can do datetime.now. If you do, we'll just suggest if you do ever use datetime, you should always attach a time zone. This will make your life a bit easier in the future. And then we can obviously do arithmetic with times. Right? We can add them, we can subtract them, we can convert them. So why does AstroPy time exist? So I actually put two areas here, but then I actually forgot the third one. So the first one is that astronomers have bespoke time formats and bespoke time systems. Obviously, Julian date, modified Julian date. I think there's U time, which I think is from well, that's technically, well, Unix time, and then there's U time. There's a whole bunch of other time formats that the standard library does not support. And you will find data in these time formats, and you need a way to convert them out. The other thing is nanoseconds. So the second one is nanoseconds. If you're an astronomer, you're doing pulsar timing, these differences in your data matter for your analysis. The third one that I forgot, and I don't know how I forgot, is leap seconds. A lot of the times, these dates are provided in seconds, accounting for leap seconds. And so when you try to do this with the standard library, you will have errors because the standard library does not support leap seconds. Leap days, leap seconds. So what I'm going to show you is that in AstroPy time, you do all the same operations as datetime as the standard library. You just have support for all of these features. So, for example, this is the modified Julian date of, I don't know, I hope of the flare. No. We get this value. I can never convert these in my head. That's what a computer is for. We can then change the representation of that time as an attribute. So we can go to Julian dates, but also we can just get back our ISO times. So we have our ISO time here, and we can have our ISO time T format. The one thing to be caught out by doing arithmetic is that if you do a time delta, it defaults to days, which I'm pretty sure is not the same as if you do a time delta with the standard library. But you can do, but to go back to units, is that you can have a unit of a day, and you can subtract that from a time, and that just works as well. Then obviously once if you want a list of times, well, NumPy also between the units supports these operations. And now we have a list. We essentially have an array of times, and we can subtract times from the first element. We can then even turn it into the unit of days. But nanoseconds, we have to be very careful, because if I create this beautiful looking time string, I print it, it's all gone. So you have to change the precision of the AstroPy time. And now we have 9 seconds. But just again, to check, you turn it to a daytime, they're gone, right? That's just and AstroPy does not tell you. I think AstroPy used to raise a warning, and then they got rid of it because people were annoyed. And so that's just an aside about AstroPy time. All of our times in SunPy are AstroPy times. So we've started with time, next onto our instruments. So through our high-level attributes, in this case, instrument, we have set up a system that tries to tell you all of the information about what SunPy supports out of the box. So if you print the instrument, like high-level name, you get the attribute name, the client that it comes from, the full name, and the description. So the difference between the full name and the attribute name is that certain names are not valid Python code. So we basically strip them out, we make them valid Python code, and we lowercase them and remove characters. But as a result, it can mean that if you look at some of the attribute names, they look a bit strange. So we provide the full name as well. And we try to give you a description of what that is. So this is all the VSO, Eve, Gong. Sorry, it's going to keep going. I'm not going to show you all of that. But that's how we try to allow discovery. I just actually opened an issue saying that we should actually make that searchable. It's not actually filterable. It just prints out the whole thing in the notebook. There are ways to make tables in AstroPy searchable, but that's something we need to work on. Oh, yes, of course. Apologies. Yes. So I spent 2 weeks of my life working on this. Okay, verifying OneDrive. I have no idea why this isn't working. I assume tab complete works like normal on a MacBook. Okay, well yeah, the autocomplete is not working at all in my notebook. That is unfortunate. Yeah, it's not working at all. Curious. So what should happen is if I press top, hopefully it'll work for you. You press dot, you press tab, a list of all of the attributes will come up. So this is dynamically created at instantiation of SunPy. You shouldn't worry about the details, but the idea is not only do we allow you to print, but we want you to search for the attributes through what everyone uses in Python, which is the tab complete, which unfortunately isn't working. Okay, just this, beautiful. Thank you, everyone. It was a pain to implement, I will tell you that. And so now we have a time and we have an instrument. We're just going to do our first. Things are going horribly wrong with my notebook. Unfortunately, you're going to have to ignore this error. It's actually not an error, but AstroPy released the next major version last week, and that broke the printing of the units in our search code. So even though there's errors, if you scroll down and ignore this, everything prints out nicely. So we're not actually quite sure what happened here, because it should break, but it hasn't broken. We don't know why. It's now patched, but we weren't able to get the release of SunPy out in time. And so this is our table. This is a very large table. So this essentially tells you what the virtual solid observability returns from if you search AA. So it tells you the provider, the wavelength, the instrument, start and end time of the observations. If it's a full disk, the size of the data, though some of it's actually wrong. One of our clients returns negative size file data, which obviously isn't real, but. And so what we're going to do is start building up this query with time. So, okay, we have an instrument that's 200 records. We're not going to download 200 files. So we're going to pick the next one is the wavelength. So as a ground-based observer, my favorite wavelengths from AA happen to be the ones that correspond to the chromosphere. So we're going to scroll all the way down. I've lost track of where I am right now. No, this notebook is not treating me nicely. There we are. So we can add a wavelength attribute. And because we enforce units, you can't put in a number here. It has to be a valid AstroPy unit. In this case, we pick angstrom because, again, it's our favorite unit, my favorite unit. And then finally, we just assign. So we just assign this query as a concatenation, just so we can use it for later. So the only difference here is that I added an extra sample data, a sample, is it not highlighting at all? A sample keyword, obviously, because AA data is every 12 seconds. If we were to query this amount of data, we would anger a lot of people. So this is going to be 12 minutes. So this will be about 5 files by the end. So we're just going to assign this, and then we're going to do that search. And I'm just going to do this. So our next exercise is just to take this query up here, call it stereo_query. And the only thing we're going to change is the instrument on stereo. And we're going to do the same search again. No idea. I will give you probably 2 minutes. I don't want to overrun. I don't want to get into lunch. What's going on? Yeah. Okay. Do you want it enabled? Don't ask again. Let's break everything. Beautiful. Just double check my codes. Don't worry. Beautiful. No, right, of course it doesn't. It cuts off beautifully. That's exactly what I need. So to ensure that I don't cut into lunch, so the only difference was to replace the instrument.aa with Sechi. Obviously, I guess I should have clarified what the instrument actually was called before I gave you the task. But again, solar physics is all about finding the data. That's half the fun of your research. You'll get used to it. Like it's. And so what we can do, so the point about Fido is not only can we build up the queries, we can then start adding them together. And so we can just take, we can just, instead of creating these separate queries, we can just tell Fido, okay, I want either of these instruments. We just do the Python OR. The rest of the query is the same. The wavelength, sample. Oh, right. And so if we ignore this error again, we now get 2 search results, one from AA and one from stereo. And so this way allows you just to start chaining up these queries into ever more complicated versions. So obviously, one of the sources I said was GOES, but GOES obviously does not have a sample or a wavelength. The GOES data is provided in a different file format. It is also provided as a day file, so you have one file for the entire day. So what we can do is we can combine our query from above. So we're just going to call it AA or SECHI. We can then create a GOES version. So we're going to use the XOS instrument. We're going to pick GOES 17. So GOES, for people who aren't familiar, they launch, I think they're still doing it, but they launch a new one every 2 to 3 years. They just increment the number. Then once the old ones decay, they just stop saving the data. And so one of the other attributes we have is resolution. So GOES provides a range of data attributes. No. Physical observations, I think. In this case, this is the flux. This is the 1 second flux from the instrument. And we can just cram this all together here like this. Time, either this query or this other query. So we're going to get all 3 types of data. Again, ignore that error. As before, we now have 3 providers, our SDO data, our stereo data, and down here, our GOES data. And so just to double check, we have 3 tables. And if you want to access any individual table, you can just index the return. So the reason to do this is that some of the data providers will give you a lot of metadata through the search query. And so, for example, if you query the JSOC, they will tell you, say, the data mean of the SDO data of each file. So you can, in theory, do like light curves through the metadata without touching a single data file. And so we allow you to access all of this data. It's just a fancy pandas, not technically pandas, but it's panda-like data frame. And you can index these columns and you can plot the data. And we'll do some of that later on. So our final step before lunch, and this is where we make someone angry. We're going to take this combined query and we're going to just save it to this path. So what Fido lets you do is you can go, okay, I want you to save this data folder, but then I want you to separate, say, the files by instrument name. You can do this through the other attributes. If you want to save it by wavelength, you can do slice, curly brackets, wavelength, and Fido will just put that in those locations for you. For now, we're just going to do it by instrument, and we're going to see what happens. And that will hopefully concludes the session before lunch, but let's give it a couple of minutes to see if we can download any data. Any comments, suggestions, thoughts before of the material so far?
So when I was looking through the top with the dot instrument, I noticed that all of them, or almost all of them, were in the VSO client. But then also above, there was a bunch of other clients. So are the instruments only grabbing from that one mostly, or can they grab from the other ones?
So by default, it will match as many clients as possible. So if you search by just instrument, and if there's 2 clients, it will provide you the results from both clients. Obviously, that is not always the case. For example, I think our Eve client returns only level 0 data. So if you search, you have to opt into that specifically because it's not science. But yeah, by default, it should be all the instruments except specific. So actually, what I forgot, while this is downloading, is so we provide a range of, okay, no. Oh, apologies. So we provide like a bunch of like extra clients that we don't tell people by default. It's more of you have to know it's there. So for example, Cedar Web, we have a Fido client for that. But by default, it doesn't tell you because we have namespaced that out from the main Fido client. Partly because there's so many data sets. I tried to print I printed the products, and it's like 1,000 lines long, blank. So those are opt-in specifically. But by general, we try to match as much as we can. Oh. Oh, okay, right. Oh, beautiful. Oh, wow, that really sped up right there. Ah, beautiful. That's what I like to see, errors. So actually, yeah, this actually takes me to a second point. So when files fail to download, we try to print, we print this message to check.errors, and this seems a bit strange because you would assume that files is a list. And files is actually a list, but it's a special list that has an attribute called errors. And it will tell you that we had some problems connected to some of the data. The good thing is that we can just run this again. We'll delete that. So Fido's caching is based on file name. So if this is a file name that's already on disk, it's not going to check. So if it's corrupted, for example, it's not going to check that it's a functioning file. It's just checking the file name. So if a file like downloads midway, actually, no, we changed that. We did change that. Sorry, we changed that. Failed downloads now get deleted. Apologies. I forgot we did that. And then we have this. And so if we do Cedar Web, hey, okay, the data set. And if we print the data set, this is a mistake, but the entire, almost the entire Cedar Web catalog can be downloaded through Fido, but you have to opt in to do so. Very long. And let me just double check the instrument as well. No, okay, never mind. Anyway, I'll stop there. I've downloaded the data. I don't know about you. Hopefully you just keep hammering the Fido download again. It'll work eventually. Yeah, and I will turn myself off.
Awesome. Thanks, Nabil. We're on lunch break now until about 5 after 2. If you're interested in Indian food buffet, I'm just going to have Sean stand up and then we can gather around. Otherwise, you are free to go wherever you like for lunch and just get back here by 2. In case you didn't hear before, it is safe to leave your bags here. You don't have to take your whole life with you. All right, everyone, Nabil's getting set back up here and we're going to start again with our afternoon session. Just a reminder, we have signups for fun activities out there. There's axe throwing and there's also some fun escape rooms planned. Sean's going to be leading up the escape room effort, so don't want to miss out on either of those. But yeah, without further ado, let's continue.
Afternoon, everyone. I hope you all had a good lunch. So I want to finish off the SunPy tutorial. So where we finished off last was we'd hopefully downloaded all the data. And if I print them, we should have something that looks like this. So it's a list of AA files through our 4 channel, our stereo data, and the final one should be our GOES data. Did anyone have any problems downloading the data in the end, or did anyone have any problems downloading the data, or was that successful for everyone? Okay, so we have all these files. Let's do something with them. We're going to start first off with the 2-dimensional files. So all we're doing here is we're just taking the files and we're just going to search for them and we're going to sort them. So if we print them, we now just have our AA files sorted by time. And we also have our stereo files sorted by time. So I'm not going to get too much into data file formats, but typically the most solid physics data are available in FITS files. And they consist of what is called header data unit pairs, HDUs. And we can open these with AstroPy. So AstroPy provides a file reader. And so we can do from astropy.io, we import fits. We then just do fits.open. We're just going to do the first file for now because it doesn't matter which file we open. And then we just print the resulting object. So as you notice, there are 2 items here in this list. I don't want you to worry about the first item, but it's a consequence of just the fact that the files are compressed. All the data that we actually need is actually in the second element of the list. So we can do this. So we can access the data directly from the file. We get this large NumPy array. This NumPy array, I think, is should be 4K by 4K. Yep, 4K by 4K. And for example, we can then import matplotlib and just do a basic visualization, as you can do with any array. So we're just going to initialize the figure, add the subplot, and so we're just going to plot the data, and we're going to set a very low vmin, vmax. And it will render, and there we are. Obviously, plt.show is normally used in scripts and not in the notebook. And then we have an upside down image of the sun that's scaled poorly, I would say. So this is how we can interact directly with the data, plot it. If you want to do some, say, you want to then crop the array, you can also do that with indices. The other part of the FITS file is the metadata. So each file contains a large dictionary of key value pairs. The problem with the FITS metadata is the keys are, I think, 8 characters max in length, so they're abbreviated, so they can be very cryptic to read. Yep. And so if I just print the header, you can see that this FITS file is actually a non-valid FITS file, but we'll ignore how valid the FITS file is. But as you can see from this this very large dictionary, unless you understand what half these keys already mean, this essentially is gibberish. Well, maybe not gibberish, but unless you have the documentation up from the data provider, which will explain what these keys mean, you're out of luck. And it just includes all of the metadata. Scroll all the way down. No. So as I've just shown, we can access the data and the metadata directly. We can index them. We can access the dictionary directly. But the problem is that it's very opaque to a user. And so, for example, it's like, I want to crop in an active region in this image. How do I work out where the active region is? Or for example, what coordinate system was this image taken in? ultimately, we need a way to tie the metadata and the data together, and that's where SunPy map comes in. So we're going to create a SunPy.map of our stereo data and our AA data. So typically, again, it's a style choice. We're in SunPy, we do import SunPy.map, and then we initialize the map by doing SunPy.map.capitalize map. We're going to pick the 6 image because I picked that randomly. And so all we've done is initialized a data container for our 2D dimensional data. And I've told you nothing else. So let's see what this actually contains. So because we're using a notebook, we can do a little trick here. We just print out the object. Apologies. We offer a quick look, what we call the quick look functionality that primarily only works. You can pop out, it will pop out a window if you use a script, but in the notebook, it looks like this. It will tell you the metadata that we've parsed, the exposure, the dimensions, the coordinate, provide you a rough image that is scaled. I forget which scaling the quick look uses. But as you can see, this is not a great looking image. You wouldn't actually want to like make a figure and give that to someone. But you can like see the different like distribution of the pixel values. And this is all done through the notebook. The other choice for now, and we'll get into plotting a bit more later, but we offer a peak methods, which tries to take the image and within SunPy we've gone, okay, it's a data file from this instrument. We're going to scale it like this. We're going to apply a color bar, a color map. And so we get this resulting image where the axes now, instead of pixel units, are in coordinate units. You get the color bar and scaling. You get what looks like a much more traditional image out. But we'll talk about visualization a bit later on. So as I was saying, we want to bring the data and the metadata together. And so we want to avoid users having to directly deal with the metadata. But if you want to deal with the metadata and the data directly, we don't stop you doing this. So you can do a map.data, like you could do with the fits data. You get the array out. And if you do a .meta, it tells you the metadata that is essentially now just a Python dictionary version of the fits header. The main difference between, say, our meta object and a fits header is that this object keeps track of what changed and what values were changed. So there is a history attached to this object that doesn't exist in the fits header. So as I was saying, it's very similar to how AstroPy fits directly allows you to access this information. But we have added a bunch of metadata attributes to our map. So for example, you can do m_aa.wavelength. It will tell you the wavelength as an AstroPy unit. If you want to know the instrument, we print out the string. A lot of these underneath are just like Python classes that we've had to wrap. We've had to massage the metadata. Creating valid fits files is very tricky to do. I think almost, if I say no one probably does it, I think it's probably fair. Like it's very tricky. There's actually no way to validate against the like there's several levels of specification. There is no actual way to verify your file against that specification yet. Hopefully NASA will write one, but for now, you just have to hope it's okay. And obviously the unit of the map as well, in this time counts. Will this change to DN? Sorry. Yeah. The unit will change. So we've tied our data and metadata together, and I guess coming up to the part of this talk where I like the least, coordinates. So within the fits, metadata defines the coordinates of the image, where it was taken, what the data provider wants you to, how the data provider has determined where the sun is and what essentially the pixels correspond to in physical space. Yeah. Sorry, so the question was, are these images publication quality figures? The answer to that is, depends on the data. So these files we download are what I think JSOC call the, and Alex will correct me, the science-ready data. So these are, if you want to make figures for publication or do an analysis, these are the files you use. We don't enforce the data you put into MAP being of science level, science-ready level or science quality level. I forget what the actual terminology is. So you can, in theory, put in like raw level 0, like straight out of the telescope data that's not being calibrated at all. We don't stop that. But what we're showing for this tutorial are the science level data. So as part of the fit standard, the observer location of basically where of what took the image and where is part of the fit standard. And so to parse that information, we use AstroPy. So this is an aside about how AstroPy underneath, or say AstroPy's public API about coordinates. So that is done through the SkyCoord object. So that lives in their top level namespace from AstroPy coordinates SkyCoord. And so I'm just going to create here. So these two next lines don't have a. They are an example of the API, but they're not an example of useful information. I'll put it that way. So I have created here a point in space using the ICRS coordinate system, which I define here as the International Celestial Reference System. Now, what that system is doesn't actually matter because it's not really used for solar physics, but because we're using AstroPy, we have access to not only all of the astronomical coordinate systems, SunPy then leverages that system and bolts on top of that the solar coordinates. And that is done, if you ever do from import, and we'll do it later on, if you import SunPy.coordinates, it will then register all of those coordinate frames with AstroPy. No need to do anything else. But the point about the SkyCoord is that it's designed to allow you to transform between points in space. So for example, I have now transformed from one coordinate frame to a galactic coordinate frame. I have no idea where this is in physical space. And this is what I'm saying about these examples being for like API examples, but not necessarily useful solar physics related. So now we get on to, again, I say my least favorite part about solar physics, coordinate frames. There is a very detailed range of papers from Thompson et al. That defines basically all of the coordinate frames that solar physics use, I think from the 2006, apologies. And so this is the formal definition of one of the frames, the Stony-Hurst heliographic coordinate system. I'm not going to read this to you, but the main thing to know is that it defines a line between Earth and the Sun. So you think about the coordinate frame as a box. You're defining the main axis in a straight line between the Earth and the Sun. And so for us to use that within solar physics, or at least within SunPy, we can import from our coordinates namespace the actual coordinate frame, or we can instantiate a coordinate frame. The thing about this is that you require, actually just ops time none. Yeah, let's find out. Yep, beautiful. Control-C. So typically this frame requires the date time of when you need to use. If you set it as none and you try to transform between like coordinate frames, it's going to error because to mathematically do the round tripping for the coordinates, you need to know where the observers are, but also when they were in time. So we're going to instantiate this coordinate frame when the flare happens, or the CB. But we haven't passed any positional. This is not instantiated in space where you are. This is just defining the, I guess, the bounding box of where you will be, or the description of where you will be. So then we combine that with SkyCoord, which is AstroPy's coordinate. So we can take, again, this point, 10 degrees, 20 degrees at 1 AU, and we've defined in space this physical 3D coordinate as a function of the heliographic Stonyhurst frame. And with SkyCoord, as I was saying, it allows you to access the individual properties. So you can find the longitude, the latitude, the radius of where you are, but also allows you to transform between components or representations. So you can have the Cartesian representation, or if you want spherical, as the frame is defined, you have that by default. Now, the second least favorite part about this, the other type of coordinate frames, which are defined as a function of where you are, or where the observer is specifically. So typically, this is the helioprojective frame. And we'll do the same thing as we did last time. We're going to import this frame. And we're just going to instantiate as a function of time. But we're saying, so much like our data, much like our Fido example, we are building this up as a series of steps. We're starting, okay, here's the abstract coordinate frame. Here's the point. And then we're going to, okay, here's this other frame that's going to be defined as a function of another frame. So that's what we're doing in these 3 lines. We're saying, take this helioprojective point at this time, attach this heliographic Stonyhurst coordinate, and then we go, okay, using that information, we define a different point in space, and we picked 6 random numbers here. And we have this kind of like complicated looking SkyCoord. It's defined in 2 different frames with 3 different points. And this is all very confusing. And the question, I guess, Your Honor, is like, what am I going to do with this? And that's where we try to abstract this out with map, because I have been doing this for 10 years now. 10 years? How old am I? 12? Either one. I've been doing this for a period of time that, you know, it's kind of scary. And to this day, I don't really understand half of the coordinate stuff. Like we have like experts that deal with the coordinates. I just check their code and they just tell me where I've done my mistakes. But we try to abstract this out towards map because this is mathematically and like conceptually very complicated. So we just go, okay, we have this data. This is the coordinate frame that was defined in the FITS file. And then you can go, okay, where was SDO, for example? And we have an observer coordinate that tells you, okay, when this image was taken, it was at this location in physical space. And then obviously we do the same for stereo, which obviously at the time was a completely different location. And so what we can do with this information is that we can try to work out exactly where things were at this point in time. So this is a large block of code. Don't worry about like the specific details. I don't want you to have to, you can have time to look at what we're doing here. But the idea is that all we want to do is generate this figure. This is a rough figure that we showed. This is a rougher version of the figure I showed in the part 0. So all we're doing is creating a polar plot in matplotlib, going, here's the sun, SDO is blue, and stereo is A. And so we've gone from this conception of like a description of points that don't really make much sense if you just look at them, to hopefully a plot that, okay, this is exactly where things were at this time. And that is the abstraction that we're trying to blend into map. Now, with those coordinates comes another part of AstroPy, which is the world coordinate system. So the only thing I want you to worry about from this part is that we have an image taken on a CCD, which has a pixel grid. If you want to, say, crop a region based on arcseconds, you need a way to transform between either your coordinates, where you say the HelioViewer image said this is at 100 arcseconds by 200 arcseconds. You need a way to translate that coordinate into a actual array indices, so you can index out just that data. And that's what WCS is essentially designed to do. As I was saying here, It's incredibly complicated. I'm going to show you like two parts of it. So this is like the metadata representation of a WCS. It defines a whole bunch of things. And if you don't know what the keywords are, the only way you're going to understand them is if you read the FITS standard. And I don't want to get into that now. But the two main things to worry about is that you can go, okay, I have this AA image. Where in physical space is the zeroth pixel? And so you can do that going, okay, .wcs.pixel to world. And because it's AstroPy at the end, you have to specify units to the command, to the function, to the method even, 0, 0, and it will spit out this. Oh, sorry, down here. So it tells you the left pixel is minus 1,200 arc seconds by minus 2,000 arc seconds, 1,200. The interesting thing about this is that if you map also provides you this information, but it is slightly offset. Oh, I thought it was offset. How did we fix that? Yeah, okay. Okay. There was some confusion. So the fit standard defines a pixel as the center of the pixel. Yeah? Yeah. Technical details though.
So, Jesus. An integer in this sort of framework, an integer in the pixel coordinate system is defined to be the center of the pixel. So 0, 0, it's kind of confusing because, well, I won't even say that. Yeah, so 0, 0 is the center of the bottom left pixel. And then if you went, so for example, if you went like minus 0.5 to minus 0.5 would be the bottom corner of the bottom pixel. But yeah, so the integer coordinates refer to the center of the pixels. Yeah.
Yep. Thank you, Rob. And so we can just do a range of coordinate transforms between world coordinates and pixel coordinates. So for example, we can do the center, so provide the center of the map. And then you can see it's the center of the array, as you would hope. But note that the center of our array does not actually align with the center of the sun. So we have enough time? 30 minutes. So the exercise here is just to quickly use the WCS to transform, to get the center of the stereo map in the pixel coordinates of the AA map. So that's the thing that we're doing when we have multiple instruments at different spatial locations, physical locations. You need a way to transform between one to the other. And so this system allows you to do that in a way that abstracts out hopefully much of the complexity once you get your head around the hopefully how to call the WCS, but also once you're in your head, okay, I'm here, I need to work out where the points like intersect in 3D space, which, I still don't have in my head. So I'll give 2 minutes. And so the answer here is just to use the fact that we provided the center of the stereo map. You can call word to pixel. And then you can find where the center of stereo is compared to AA. In AA, I apologize. So I understand that's kind of probably not the best explained. So I want to pause here and ask any questions, concerns, confusions. Microphone, please. Anyone? Thank you, Alex. And Will will probably have to answer for me.
Hello. I was just wondering what applications this specifically would be useful for, because I'm having trouble really understanding like visualizations of this.
So I will actually touch about the visualizations about this in the follow-up. But for example, if you have, so you've got AA, which is pointing directly at the sun, you've got stereo here. You want to work out, is this active region that I'm seeing at this very different observer location the same as AA? And so
Like the same active region?
Yeah, the same
Okay,
active region.
gotcha.
So for example, this will be done like, say you have loops. Say you see a loop on stereo of the limb. We're going to go, okay, can I see, where would this be on AA? And so that transformation is what this enables, is that you can go, okay, this loop, if it exists, should be this part of this image, of this other image.
Cool, thank you.
What would happen if stereo were on the far side of the sun and so we couldn't?
You should get nans. I think it would just return nans. I don't know if that's actually, or because it wouldn't.
You should get back a coordinate in 3D space, so it will know that it's, even though it's not visible in your image, your coordinate will, like your physical coordinate will know that it's what am I trying to say? That it's on the backside of the sun. And there is now functionality within SunPy. So there's on these helioprojective coordinates, there's an is visible method that will tell you if it's behind, basically if it's behind the limb, if it's obscured by the disk. Yeah, and it will return to you like a Boolean that says, is visible, is false. Yeah.
Thank you. Any others? Is there Slack or?
Yeah, this is a great presentation. I really value it. I was wondering, say for whatever reason, we want to create our own WCS system for a given image or a patch of image. How would we go about that?
I think Will will have to correct me, but I think our best, I'm thinking make fits header from, where is that functionality?
Yeah, so if you want to, so the WCS in like the case of these images is created from both the projected coordinate system that you're in, things like the scale of your image, the rotation of your image, and all those are pulled. Well, in general, that system is pulled from a fits header. So the easiest way to build a WCS in this case is to build a fits header. And so there is this is the function that Nabil is showing right here, is basically a way to build a fits header from more intuitive objects. So you can if you zoom in a little bit, Nabil, you could, I know this is not the most like pedagogically great way to do this of just looking at a doc string, but you put in the shape of the thing, like the shape of the data, a coordinate that describes what the reference pixel is, or the reference coordinate rather, and then there's also other more optional things like things like the scale, and then the output of that is just some like big blob of Fitz keys. And then you can pass that into a WCS, and then you can get something that you can do all these world to pixel to world operations. So this is useful, like in the stuff that I've done in the past, this is really useful if you're building like a simulated image, right? And you're like simulating like, I don't know, stereo or some like other spacecraft that's like flying around at some position that doesn't actually exist. You can then use this to just build a Fitz header, and then you can use SunPy to do all your analysis in the same way on your simulated images that you would do for your observed images. Yep.
Yeah, we have a simple, we should ask Albert to make a more complicated example, but we have a simple example at the bottom. And by simple, I mean the WCS it creates is simple, not that what we're doing is simple. Back to 100. Okay, I have 20 minutes left, so I'm going to blitz through some of this. So much to do with our metadata, we also try to provide some helpful methods for displaying your data. So our typical methods that we suggest is, so we've shown .peak. Eventually, that will not exist. But the main one is plot, and this, as the text says, automatically creates a figure, displays it for you. In this case, unlike the peak object that we had before, there's no color bar. It's just the raw image, color mapped, scaled, axes labeled, and a title. So this is also leverages AstroPy. So underneath AstroPy provides a bunch of code that basically uses matplotlib to do all of the coordinate stuff, all of the coordinate transforms when you're doing any plotting. But because we're providing a wrapper around matplotlib, essentially all of the plotting, a lot of the plotting API will, for map.plot is the same as axis.imshow. So you can pass in the keywords. So that's what I'm doing here. I'm just passing in a different scaling. I'm scaling from 0 to 500. And I'm now drawing a grid, the grid onto the image, and I'm passing in the same, this should be 0.5. These are essentially similar keywords that you would pass to matplotlib if you want to change the line width. So now you get a grid projected onto the image. So again, these plotting codes are just as an example of how the API works. They're not necessarily a way for you to they don't provide like a direct amount of understanding, but it's like, okay, you can do this with a plot, or you can do this with a plot. You don't have to. When it comes to like creating matplotlib images, for people who are not familiar with it, it can be a very time-consuming and very trial and error process. Between looking at the matplotlib documentation, the WCS documentation, the SunPy documentation, working out exactly where you have to be to tweak this parameter or tweak that parameter, not very clear. And so this code is just like, okay, if you want to change, say, the axis labels, this is where you need to go. Just think of the code like this. It's just an example. So the main things I want to say is that, so that grid I created before, you can just set the tick labels, and you can, I don't know why you'd want to do this, but you can create a grid that looks like this. And you can change the axis labels. And this is all just a matter of trying to make sure you've got the correct matplotlib argument to, or the correct object to pass the arguments to. And so AstroPy also provides a whole bunch of visualization. Oh, sorry.
Is it possible to change the? Is it possible to change the units of the axis as well, instead of arc seconds to, I don't know, solar radii?
Would you want that? Sorry, I guess I'll answer your question with a question. Would you like that to be done automatically, or would you? So you can manually change the axis labels. So I can. So you can manually change the axis units. I forget what the command is, but.
Because I don't remember, but there is an easy way to move from arc seconds to degree, but I never found an easy way to move to solar radii, for example.
I'm pretty sure there is an API, but off the top of my head, I cannot for the life of me remember. Hold on. There is a way. So obviously what I meant by my question was that you can obviously change the units when you create the map. So they're always in those units. So you don't have to change that after when you're plotting. Mm-hmm. All the other choices that there is definitely a way to change the units when you're plotting. I just can't remember. No, I'm trying to remember if we have an example that does this. I will say we tried to keep a collection of gallery examples on our documentation that say you just want to make a mask for a LASCO image, or you want to find bright regions in an image. I'm pretty sure somewhere. No, I'm not sure. I think we have one. Is it that one? I will have to get back to you. Yeah. There should be a way. I just need to find out. Back to this. So AstroPy provides a bunch of like normalization options. So obviously, if you want to make like a ridiculous looking image that's scaled like this, you're allowed to. So we make use of a lot of these tools internally in SunPy to ensure that our scaling is correct. Or if you want to say clip the data, underneath we're just using AstroPy to do all the mathematics. And so I have a quick example here, a quick exercise. Take this plot here and just change the color map. With knowing the fact that the keywords are the same as I am shown. If you know what the keywords are. If you don't, unfortunately, that's the other thing about Python looking through documentation. And the matplotlib documentation, beautiful. No, I don't think this is the correct one. And so just because I think I'm short on time, I will. So all we need to do is just pass in CMap, which is a keyword arc to IamShow, and you can get this beautiful, beautiful AI image. And so again, this is just another plot. So when it comes to like creating quote unquote like publication quality figures, it can involve a lot of code, a lot of like calls to matplotlib. And this is just an example of like, okay, we wanted to create this plot. And it's a lot of code just to, do this, essentially. A lot of people struggle with matplotlib, and that's totally normal. I still struggle to this day. So going back to our coordinate discussion, well, I'm showing you images of the sun, but it's like, okay, how do I combine coordinates and plotting? So I'm going to get some coordinates from a database. So this is the HEC, the Heliophysics Event Knowledge Base. So the idea is that it is a catalog of metadata for active regions, flares, the strength, the locations, the start time, end time. And so much like our previous searches, but this time this is just a purely metadata search. We're just going to go, okay, using these attributes, we're going to select a flare. FL is the shorthand for a flare. We're going to go, okay, the ghost class has to be above 2.5. So we can do this search. And, oh yeah, oh God, I forgot it does that. Apologies. So they provide the URL and the table just keeps the columns like that. But the HEC provides a lot of information. I'm just going to keep scrolling all the way to the end. And so this is like information that you can in theory work out where the flare is, when did it start, when did it finish. Unfortunately, this table representation is not the best, but we're actively working on fixing this in a summer project that we're running right now. So I'm just going to follow down to the columns that we care about. So because this is just essentially a pandas-like data frame, we can just index the result and go, okay, I just want these columns: the event, start time, end time, peak time, and the coordinates in HPC, helioprojective Cartesian. And I go, okay, now we have a much more manageable table with this information. So now that we have this information, we need to then do essentially a coordinate transform. So we need to know where Earth is at the point where these flares happened. We're then going to create a coordinate frame, as we did before, saying this time where the event happened. The observer is Earth, because obviously when the catalog is human observers at Earth. And then we're going to take that information that was provided by the HEC, which is this HPC-X, HPC-Y. And we're just going to say, okay, this is the coordinate, this is the sky call, this is the AstroPy coordinate class that holds all this information that we're going to use later on to do some plotting. So we take this coordinate information, so we're just attaching this to a list. This list is just a list of sky chords. And then what we do here is we go, okay, take this, so we're just creating a plot as normal. We're just clipping the intensity. But what's happening here is that we're using this plot coordinate method on the axis, which just takes us a sky chord and will then work out where it is on the sun. So for example, the 3 flares that we saw, we can then go, okay, these are the locations on both, not only AAA, which was observed in Earth that aligned with the HEC result, we can go, okay, these are the locations in stereo, which is on the image on the right. So for this system, we've gone, okay, we know exactly where on both images the flare location happened. This is a slight aside. I will zip through this. So we downloaded a series of images. And obviously, most people don't want to work on just one image. So this is our map sequence class, which you create the same way you would create a map, but you have pass a keyword called sequence. You just set it to true. And it basically creates a list of maps for you. And what we can do here is we're just going to make an animation. So we're just going to scale the plot, because otherwise the intensity will be fluctuating. So we need to make sure that they're kind of normalized. You don't need to worry about the details. And then we have these 2 blocks. So traditionally, this first block is how you create a plot. Because it's a sequence, it will return you an animation. Because we're in the notebook, I think the only way to display an animation is to use this magic code, give it a sec, and now we have an interactive animation. Because it's 6 frames, just to reduce the data download, you don't see much. But if you were to download the original, like 12-second cadence data, you would see a much larger event. But you know, you can just about see. It's probably not showing up that well in Zoom either. And so just to finish off, almost finish off. So we've tied our data together, we've tied our coordinates together, our visualization into a map object. So we also provide a range of like, I wouldn't call them data analysis, but I guess like data manipulation techniques. Our main one, which is our most popular, and is our most popular example in our documentation, is rotation. So if you use HMI, the heliospheric magnetic imager. Higher size model, thank you. Wrong thing. Those images are actually upside down. If you plot them, they're upside down. Just an artifact of how the instrument, the satellite was made. So our most popular example on our documentation is how to actually undo that rotation. So by default, if you just call rotate, it will just align the image solar north using the metadata stored within the FIT file. The trick here, so this is required because the default for a rotate, so when you rotate, you don't necessarily get the same size image back. So it might have to pad the array to mathematically do the rotation. By default, we set that to NaN. The problem with that is that a lot of these arrays are actually integer. So you can't pass in a NaN is not a valid integer. So here we're just going, okay, any missing values from the returned rotation, just use the minimum of the map. And so we do a plot where we just rotate the two, and then you can see the slight rotation, the very slight rotation corrected for it's very slight, but you can just about see it. And this will show up in our rotation matrix metadata, which just maps that information from the FIT file into this property, and you see it's updated. It's now essentially Unity. So we're gonna have a quick example. Just let's rotate this image 45 degrees. And I will give you a couple of minutes. A question online. Can we save the animation as a movie? Right, because you return the animation object and you pass it to PLT. Does PLT save work with the animation object directly? Well, there's a reason Will's the lead developer of SunPy.
It's that animation thing that was returned above is a matplotlib func animation. So this .2js HTML, that's a matplotlib thing. That has nothing to do with SunPy. So yeah, this func animation, and there's a save method, and you can write that to an MP4, if you have FFmpeg installed. There's various ways that it'll default to there's a lot of matplotlib docs for writing out func animation objects to movies. So that animation thing that map sequence is returning to you is importantly not a SunPy specific thing. It's now you're in matplotlib land, and you can do anything you are able to do with Matplotlib with that object.
Oh, there we are. Man, that is disgusting levels of compression. Yeah, so I had to save it as a GIF. It uses pillow because FFmpeg wasn't available. And there we are. And so our exercise to rotate, so we just do the same line as before. So the answer was just you pass in an angle with a AstroPy unit. I actually don't know why that's there. And so I then just I do the plot again, but I add the grid just to make it very clear that we're now rotated by 45 degrees. So our second, I'm going to zip through this. So our other thing we provide is cropping images. So for example, AA provides a full disk image. You don't necessarily need a full disk image. So we've calculated this out beforehand, but we've basically worked out the region of the sun that actually has the CME. We've picked the values here. We've created, so like before, we create our sky codes, specifying long lat, the radius of the sun, and the frame that we want. So the other thing about sky code is that not only can you instantiate the frame directly, you can actually use a string. AstroPy will then work out what you're referring to, and if you have all the keyword arguments that the frame requires. And then you can just pass this into submap. And we now have the cropped in region. This can also be done in pixel coordinates, which was in this exercise, but because we're short on time, I'm just going to run this instead. But for example, you can change them as long as you specify that the inputs are in pixel units. It will know that you pass them in pixel units and then crop that way. And so we have exactly the same image, but this time cropped as a 5 pixels. So our other data container within SunPy is our time series. It's our slightly neglected class, but what we will do is quickly run through this. So we had that goes data that's served as one file for the entire day. And we can then just load it into time series the same way we do for a map. The only difference is the import is different. And give it a second. Beautiful. And much like our map images in the notebook, we have this nice. We try to have a nice visualization for each channel within that file. And much like map, we have a .meta. The difference here is that metadata for a lot of time series data, because the file format is different and varies. Typically, like mission for mission, there's no one standard for metadata that I'm aware of, at least. So we try to cobble together what we can from the actual file, trying to read the mission documentation. If you don't want a time series, but you want, say, an AstroPy table, we offer helper functions to get to AstroPy table. Or more commonly, pandas is very good for time series style data, tabular time series style data. We allow you to export to pandas, assuming you have it installed. But because underneath it's essentially just tabular data, we provide all the methods that you would expect on tabular data, columns, units as a functional column, obviously metadata like observatory. But the more interesting thing is that now that we have the metadata from the HEC, we can then crop this time series to just our event. So we're just going to truncate using the API of time series. Apologies, I'm going very fast, and we can go, okay, we're going to crop from the base start of our observation from stereo and from our last date of our stereo data. Ignore the bins. And we have our light curves cropped to match our two-dimensional observations. But it's still not like the prettiest flare-looking data. So we can crop in even further. We can just create a plot, and then using Matplotlib's syntax, we can just go, okay, crop it. Don't crop the data, just crop the plot to this start time and this end time. And again, not the best. But we are literally guessing. We are looking at this time series. Okay, we think it's here. We think it's there. Can we do better? And the answer is we already have this information. So we can combine the metadata we downloaded previously and our time series data. And so what we do here is we go, okay, we're going to plot the time series as is. And I'm going to take the metadata that we took from the HEC and just plot spans where the flare, the start time, the end time of the flare, and we can get, as we saw, 3, because there were 3 in the HEC, we have 3 regions. And so by combining, so one of the dreams or goals of SunPy is to enable the combination of the metadata, the data, our external metadata, all into one set of coherent structures. We're not there yet. We probably will never be there, but that's our dream. And this is just a glimpse of hopefully where, things will be in the future. And so in conclusion, I will stop there. I will just say that, as I was alluding to before, we try to keep an extensive example gallery of examples of fetching data, plotting. If you want to do co-alignment, we want to do like co-alignment and coordinate transforms. We have extensive documentation trying to explain as much as we can to a wide audience as possible. And I will leave it there. Any questions? Mm-hmm.
Could we get our work on the example gallery?
Yes. Yeah, I will give you this warning. So our example gallery pull requests tend to have the most comments. They tend to be the most reviewed because once you have a bunch of, too many cooks in a kitchen and all that. But we will walk you through any step. I will personally walk you through any step to get a pull request to SunPy. That is an option. That is an offer to anyone here, by the way, just in case. So if you want an example gallery in SunPy, we'll get you that.
We had one question on Zoom. The question is, after performing the rotation, is there a way to remove all the off-limb pixels and keep only the solar surface pixels?
Yes. I actually do this to make some JPEGs. I do not know I can't, off the top of my head, I'll have to answer that question in person. Well, I have to work out the line of code, but yes, we provide some utility functions. Okay, what pixels are actually on disk? You can then just like crop them out, but I will answer that online.
Okay, cool. Yeah, we have the SunPy Slack that you can go into.
Yep. So please, whoever asked that question, it just says anonymous here in Zoom, but please post that question to the SunPy channel in Slack and it'll get answered later.
Oh, we actually have, sorry, we have the opposite example. We have the, yeah, I'll shut up.
Any other questions? Okay, well then we have our last break of the day now. We'll come back in about half an hour at 3:35 and we'll finish up with the PlasmaPy introduction from Nick Murphy. Okay, it's 3:35. We're going to go ahead and get started again. So we now have up PlasmaPy being presented by Nick Murphy.
All right. So yes, thank you everyone. Really great to be here. And for the next hour and 25 minutes or so, we're going to go through PlasmaPy. I'll start with a few slides. So first want to start by thanking a whole bunch of people. We've had probably about a total of 125 contributors to PlasmaPy over the last 5 or 7 or something years. And also thanking PyHC. PlasmaPy was directly inspired by AstroPy and SunPy. So thank you to everyone who contributed those or part of their communities. And also some exciting news, Elliot Johnson, who contributed a lot to PlasmaPy for his thesis research, graduated last Monday with a PhD. So yay, Elliot. He's on vacation, but I'll tell him that you all said congratulations. So, all right. So the mission of the PlasmaPy project is to foster the creation of a fully open source software ecosystem for plasma research and education. So it's pretty similar to the mission of PyHC overall, but with like a more plasma physics-y focus. So why PlasmaPy? And the reason is, I'm going to probably keep moving these things around, because plasma science is awesome. Oh no, what did I do? Okay. So those of us here probably know that plasma physics is essential to heliophysics. Like we couldn't do heliophysics without plasma physics. And also, almost all of the baryonic matter in the universe is in the form of a plasma. And I've heard some plasma physicists say that plasma should be the first state of matter because of how common it is, and because chronologically it was pretty much the first state of matter also. So plasma physics is also really vital to fusion energy sciences. And there are a couple of different aspects to fusion energy. The first is laser-produced plasmas. So things like the National Ignition Facility, where they take, I don't know, like 70 or 100 or something lasers, shoot them at a pellet containing tritium and deuterium, get it to implode and explode, and get a lot of fusion power out that way. And they set a few records for that in the last year or two. So it's pretty exciting times. And this is called inertial confinement fusion. And there's also magnetic confinement fusions, which is a lot like a magnetized donut. I really like emojis, so bear with me. And in tokamaks, you have really strong magnetic fields confining the plasma in a toroidal device and getting a lot of fusion that way. And there have been a lot of really significant improvements and investments in fusion energy in the last, in the last few years. There are also aspects of plasma technology, which I only began to learn about after getting involved with PlasmaPy. And one example is spacecraft propulsion, things like Hall thrusters and plasma thrusters, which is pretty cool. It's a pretty active area of research. One of the coolest things is plasma-based water purification, where you have water and you have it interface with a plasma. And then this is like a room temperature plasma, but the electrons are really high energy. And because of that, they're able to break the bonds of a lot of complicated bad organic compounds. So you can do a lot of water purification with plasma. It can be fairly low cost too. And there are also medical applications. So one example is using plasma to sterilize wounds. And there are also efforts to use plasma to treat cancer. So there's a lot of really cool plasma technology. And PlasmaPy doesn't cover all of these, but these are all within the scope of what we want PlasmaPy to become. Let's take some highlights before going into the tutorial of a couple of things that we can do with PlasmaPy. We'll talk about today creating particle objects and then collections of particles, particle list objects. We can also calculate plasma parameters. So things like the NRL plasma formulary. We have a huge fraction of the formulary functionality in PlasmaPy. An undergraduate recently revamped our particle tracker. So we have capabilities to track particle motions in electromagnetic fields. We also have a couple of classes for plasma wave dispersion relations. So things like two fluid plasma waves and also MHD waves. An undergraduate a couple of years ago also added a prototype magnetic null point finder. So magnetic null points are locations where the magnetic field equals 0, and they're important reconnection. So the student added a way to find these locations within a simulation cube. What Elliot worked on for his thesis was calculating the thermalization ratio of plasma in the solar wind. So protons and alpha particles start off near the sun at very different temperatures. And the functionality that Elliot wrote was to calculate how the temperature ratio changes over time as the plasma moved away from the sun due to Coulomb collisions. So pretty neat stuff. He was able to say during some of his talks, I challenge you to reproduce my research, which goes back to what Alex was talking about this morning. We also have a few classes for plasma equilibria. So one more undergraduate added hair sheet equilibria and also force-free magnetic flux rope. So things like the Lundquist solution. And then there's also functionality for analyzing data from a couple of different plasma diagnostics, including for high energy density physics. Some really cool stuff there. So I also want to mention that we will be having our first in-person summer school this summer at the end of July, beginning of August at Bryn Mawr College. This will be a little bit like the Intersect training that Alex mentioned early today, because we're going to focus primarily on how to contribute to PlasmaPy. And even more broadly than that, how to contribute to open source packages more generally. I'm wondering if PyHC could possibly have a summer school like this also on how to contribute to packages. Putting these on is a lot of work, so thank you to Julie and everyone who has been doing that. But we do have travel funding available, and applications are due this Friday, and also space is limited. In the PlasmaPy channel on Slack, I put a link to get more information about the summer school. So I encourage you to check it out. Okay, and so now, if I can figure this out, we'll go to the tutorial. And so the location of the tutorial, if you go from the top level to summer school, the Git repository that you cloned, and then PlasmaPy tutorial. And there are 2 of these. And I can't actually go back further. I can, okay. And the one we want to open is PlasmaPy tutorial.ipynb. Okay, the other notebook contains everything filled out, but this one we can all follow along. All right, so again, thank you for coming. And in this notebook, we're going to cover very briefly, in case anyone who missed this morning, we're going to do 3 lines or so of AstroPy.units, and then move on to my favorite subpackage within PlasmaPy on PlasmaPy.particles, and then calculate a few plasma parameters. Let's see if I can scoot this over more. I don't know. Doesn't seem like it. Okay. So we're going to start with a couple of imports, and we'll probably repeat those, but we can press Shift-Enter to execute the notebook. All right. So as we mentioned earlier, we usually import AstroPy.units as U. So import AstroPy.units as U. I'm used to an ergonomic keyboard, so typing on something flat, there are going to be a lot of typos. All right. And the way that we use AstroPy.units is to take a number or array and then multiply it by a unit object. So we can take 60 times u.km to get 60 kilometers. And so what this does is create a quantity object, which is a number, sequence, or array that has a unit attached to it, which is incredibly helpful, I found. And we can also do operations with unit objects to get quantities with compound units. So we can do something like 88 u.imperial dot mile. Whoops, yeah, dot mile divided by u.hour and shift enter. So does anyone remember the 1980s? So yeah, this was a bit inspired by Back to the Future. So if anyone has a DeLorean, DeLoreans are powered by AstroPy.units. Okay. And AstroPy.time also, probably. Okay. So now we can move on to PlasmaPy.particles. PlasmaPy.particles is probably the most broadly applicable of PlasmaPy's functionality. So it's really worth taking a look at. Let's do an import. So let's do from PlasmaPy.particles import star and shift enter again. So there are a bunch of different functions within PlasmaPy.particles to calculate different plasma parameters. So the input of these functions is a representation of a particle. So let's calculate the atomic underscore number of, and let's use the atomic symbol as a string, of iron. And we get that it's 26. Good. The universe is as it should be. We can also provide a number which would represent the atomic number. So let's do element underscore name and then 26. And we get iron back for that. And we can also provide standard symbols or the names of particles. So the inputs for functionality in PlasmaPy.particles is pretty flexible. So we can do is stable, and then in parentheses, E minus, and get true, an electron is stable. We can even do this without the minus and get, again, that an electron is stable. And we can also get the charge number, or often called the integer charge, of a proton, and we can spell it out this time. And so a proton has 1 times the elementary charge. And we can also represent isotopes by providing the atomic symbol or the element name with a dash and then the mass number. So if we want to get the half-life of carbon-14, we get that it is 1.8 times 10 to the 11th seconds. And we can even do this as spell out carbon. And if we want to represent an ion, which we do pretty often in PlasmaPy, in plasma science, we can do something like charge number, and then an atomic symbol. So let's say iron, and let's say iron 56, so that particular isotope, and then 13 plus. And then shift enter, and we get that the charge number of iron 13 plus is 13. It's a good sanity check. And the functions that we have in PlasmaPy.particles are quite flexible in terms of the string inputs. So we call an input particle-like if it can be used to represent a particle. So let's get the particle underscore mass of iron dash 56 plus 13. And then shift enter. And we get 9.3 times 10 to the minus 26 kilograms. We can also do particle underscore mass of iron dash 56 plus 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 plus. See if I counted right. Yes, okay. There's one saying during live demos, which is never do live demos. So let's proceed on with this live demo. Another thing we can do to provide particle inputs is use the Z keyword argument to represent the charge number of an ion, and mass num to represent the mass number of an isotope. And so these arguments, like we often have them keyword only to avoid ambiguity. So let's do particle mass again. And then iron dash 56. Oh, sorry, iron. And then Z equals 13. So I'm including the Z here. And then mass num equals 56. Then shift enter again. And we get the same mass. So these are all different ways to represent ions and isotopes in plasmas. Oh, could you use the microphone? Someone has one. Oh yeah, please do ask questions.
Do you know off the top of your head how to convert to atomic mass units? I can't think of the
Let's see if I do.
AstroPy unit.
Is it? So
You do .2, but then I can't remember.
U?
U dot something. U dot U? Oh, okay, thank you.
Cool. Awesome, we did it together. Yay, go us. Cool. So yeah, one of the nice things about these live demos, apart from the potentiality of everything breaking, is that you can try things out at the moment, and occasionally I'll forget how to do something, and yeah, we can figure it out together. Okay. So yes, please do feel free to ask questions, and over Zoom also. And I think Sean will be monitoring. I might have just volunteered Sean, but you're good? Okay, cool. So up until now, we've used functions to get different particle properties. And the particle properties that we got from these functions are all AstroPy quantities. So they're all using AstroPy.units. But PlasmaPy also has a particle class, which we can use to create particle objects. All right, and so let's create a couple of these. So let's say proton equals then particle with a capital P. And then let's do P plus. And then I'll do a regular enter. And then electron equals particle electron. And then finally, iron 56 nucleus equals particle. And then again here, we can do Fe. And then Z equals 26. And mass num equals 56. I knew that. Okay. And now shift enter. And these commands created a proton object, an electron object, and an iron 56 nucleus. As an aside, one thing I try to do is to think of the length of variable names, not in the number of characters, but in the time it takes to understand what the variable means. So thinking of it in terms of like seconds, there's one, I think it was like LAPAC has a function that's something like DZPCDF or something like that, which is a short number of characters, but very long in how long it takes to understand. So names are important.
Nick, we have one question.
Oh, please.
Oh, here. Could you repeat again? You started off by explaining what was the purpose of, like, what's the point of particle objects, or what are we doing exactly?
Okay, so the point of creating particle objects is to have an object that represents a particle and that we can use to access the properties of those particles. And so when we do this, there are a lot of really cool things that we can do using like the power of Python. So we'll start. So one of the things that we can do is to get the mass. So proton dot mass, and then shift enter, and I get 1.67 times 10 to the minus 27 kilograms. We can do electron dot charge number, and then shift enter, -1. So electron is -1 times the elementary charge. And then we can also get electron dot charge. So if we wanted the charge in physical units, so shift enter again, and we get the charge in coulombs. And there are even attributes like iron 56 nucleus dot binding energy. One thing I want to change, the notebook feature. So shift enter, and we get the binding energy of an iron 56 nucleus. And we can change that. So this is an AstroPy quantity, so we can change it to, let's try GeV. I'm sort of winging it here. So the binding energy of an iron 56 nucleus is about half a giga electron volt. PlasmaPy, for the most part, we try to use SI units throughout, though we try to have our functionality compatible with like the conventions that plasma scientists often use, like talking about temperatures in terms of electron volts. So if a PlasmaPy function asks for a temperature, you can include it in electron volts as well, but it'll return temperatures in Kelvin. Okay. So there are also some useful attributes. So for things like fundamental particles, like an electron, we have an attribute for anti-particle. We can do shift enter, and we get that the antiparticle of an electron is a positron. And one other neat thing we can do is use the tilde operator on a proton. Still getting used to this keyboard. And get that the antiparticle of a proton is an antiproton. So in software engineering, there are different techniques like test-driven development, where you write the tests first and then write the functionality to go along with it. One of the software engineering practices we've pioneered in PlasmaPy is procrastination-driven development, where there's something that you need to do, but you really don't want to, so you do something that's a lot more fun. And so this is one good example of procrastination-driven development. I highly recommend it. PlasmaPy actually started as a procrastination-driven development project. So long history of that. Okay. So the next things that we can do, let's create a deuterium object. So we do deuterium and then particle, and let's say D0 plus. And then I'll do a regular enter again. And then let's do deuterium dot ionize. And now we can do shift enter. And we get, instead of deuterium, like a neutral deuterium atom, we get a deuteron, a deuterium ion. We can also use this, we can provide, we don't have to ionize or recombine it by 1, we can provide a number to it. And then do, if we want to create an alpha particle, so alpha equals particle alpha, and then regular enter. We can do alpha dot recombine 2, and we get a helium-4 neutral atom. Okay. So far we've talked about particles that actually exist, but sometimes we want to have a particle with custom properties. And for that, we created a custom particle object. So we can create a custom particle. I'll not follow my advice and use CP as a shorthand for custom particle. So custom particle. And then let's say 9e minus 26 times u dot kg. And then 2.18 e minus 18 times u dot c. And we do want to keep track of this, so let's provide a symbol equals Fe 13.6 plus. So this would represent something like an average ion. Oops, shift enter this. All right. And we can use custom particles in much the same way as regular particles. So we can do something like cp.mass to get the mass back. We can do cp.charge and get the charge that we provided. And then cp.symbol, shift enter to get the symbol that we created. So one of the things, oh, right. So if we don't provide one of the mass or charge, so we create a custom particle with just the charge, so like 9.27 e minus 26, oops, not the mass, times u dot kg. So we provide a mass to it, and then we want to get the charge from this. We get not a number, coulombs. So we'll be covering PlasmaPy formulary a bit later. And one of the things that we've been making progress on in PlasmaPy has been making the functionality compatible with things like custom particles. So for most of the most commonly used functions within PlasmaPy formulary, we can provide custom particles to it and it'll still work. Not everything, but we're making progress. And thus far, we've created single particles, but plasmas usually contain multiple species. of particles. So let's create a particle list object, which is essentially a list that contains particles. Say iron ions equals particle list. And then in the parentheses, we want to provide, we want to make it a Python list. So we enclose the inputs within square brackets. And then in that list, we do FE 12 plus, FE 13 plus, and FE 14 plus. All right. And forgot a bracket here. I can do Shift Enter and got an error. Okay, so one thing I've learned over many years, and I'm still learning, is that error messages are more useful when you actually read them. So long lesson, hard lesson to learn. So in this case, it says invalid charge information about a particle. And the problem here is that I had a space. So I'll scroll back up. And a nice thing about a Jupyter Notebook, you can re-execute cells. And in this case, it worked. Yay, good. So we created a particle list containing iron ions. And particle lists also behave much like particle objects. So we can do things like iron ions dot mass and get the masses of the different ions. So iron 12 plus through 14 plus. We can do iron ions dot charge and then this. So you get the charges as a quantity, AstroPy quantity array in units of coulombs. And then iron ions dot symbols. SYMB. Okay. And so we get the symbols that we provided to it. Another thing that we can do once we have particle objects is use them to create a particle list. So let's try proton plus electron and Shift Enter, and we get a particle list containing a proton and an electron. And we can also get an average particle. Let's do iron ions dot average particle. And this is a method, like it calculates the average particle based on what's in the particle list at the time. And we get a custom particle that is the average of the ions that are contained in the particle list. So it's essentially like an iron 13 plus ion. Oh, please. Oh, right.
Sometimes when you are doing the dot something, you don't pass the parentheses, and then with this one you do. What's the difference between doing that?
Oh, that's a very good question. Important question. So there are, for Python objects, there are both attributes and methods. And so an attribute is essentially an object that is tied to the other object. So in terms of charge, this is returning an object that is stored within iron ions. And it's not doing like a calculation to get that. The parentheses here are because average particle is a method, essentially a function that is attached to iron ions. And in this case, it's doing actual calculations to get the average particle. And I think, let's say, help of particle dot mass, and then shift enter. And so in this case, it says that it's a property, which means that it's like an object that's attached to particle. But if we do help for average particle, and shift enter again. Oh, okay. Particle list. Then it will have documentation that shows what the different arguments you can provide to it are. So using help on these different things is a good way to go about it. Then if I remember correctly, for most of the functionality, we provide examples of like creating a particle list and then like using it to calculate. So going through the documentation is a good way to like figure out which ones are properties and which ones are like the methods of functions. Yes, that's a really important question. Okay. Cool. I always feel good when I improvise and things work out. So.
Hey, Nick, we have a question that came through on Zoom. If you want to improvise an answer. Question is, could you explain the logic behind the upper lowercase and the use of shortcuts? The examples being like mass_num/z when you are using function class member functions, etc.
Oh, so like the case of the parameters that are provided to a function. So like z and mass_num.
Yeah,
yeah, it's quite confusing when you're writing it out, when you're spelling it out, when you are using shortcuts, when you're capitalizing a parameter, the rationale why you're using, for example, why you're directly accessing member variables rather than using an access function, this kind of stuff. It's yes, you can look it up in the documentation, but it's obviously impossible to find.
Okay, yeah. So we do have a couple of conventions in PlasmaPy where we usually represent the charge number, like the integer charge, with a capital Z. And so this is along the lines of notation that is often used in plasma science. So it's essentially with the capital Z, we're trying to be consistent with what's used in the field. And so for this, we also have mass_num, and we don't spell it out completely because there's a function called mass_number, which we don't want to overlap with. So those are some of the reasons. And usually in Python, it's best to have lowercase with underscores between words variables. But because it's often like a capital Z in plasma physics, we ended up using that. So same with like a capital B for magnetic field. So, but we do try to be consistent within PlasmaPy. And we've made some progress on that, though there's still a few places where we're not.
I want to make the comment that naming things is always hard, but that was such a meaty answer and way better than I think most packages would have thought through their named stuff. So thank you, Nick.
It's naming things is, oh, it's tough. Like PlasmaPy.formulary, I think it took us a year to think of that name. And PlasmaPy.particles, again, I think it took a year. It used to be PlasmaPy.atomic until we realized that there were particles that were dot atoms. Turns out. Please.
Just one more comment on that. You can always use private properties and whatnot to handle it internally, right? And make it more transparent for the user. Are you planning on doing that?
Oh, we do have a lot of private variables within like particle class and things like that. So we do make use of that a lot.
Yeah, but like what I mean is you can set that to be mass number and that use mass num or something in the code internally.
Oh yeah, and another thing that we can do is to have like mass number underscore at the end is another common convention.
Right.
So in this case, we, I don't know, 7 years ago decided on mass num. So the most important thing is consistency so that we all know what to expect. So yeah, thank you for the questions. These are really helpful. Okay. All right. So another thing that we can do, and this functionality, I think was first suggested by Stuart Mumford, who is one of the SunPy core team. And this was maybe like 2018 or something, 2017. And let's calculate the energy of a nuclear reaction. And in this case, we can use the greater than sign operator. So let's create a few particles. So a deuteron equals particle, and then D plus, regular enter. A triton equals particle T plus. So this is a singly ionized tritium atom, which I looked up once and thought it was cool, so I keep using it. And then alpha, which is particle, and then let's type out alpha. And then neutron equals particle N. And then shift enter. So created a deuteron, a triton, an alpha particle, and a neutron. And let's get the energies. So let's do energy equals deuteron plus triton. And then, this is where the magic happens, a greater than sign. And then alpha plus neutron. So this represents a nuclear reaction, the one that is most sought out in fusion reactors. Let's press shift enter to get that. And then let's convert this to, this is returned an AstroPy quantity. So energy dot 2, let's do m underscore e, or it's lowercase e, v. So mega electron volts. And then shift enter again. And we got the energy of the nuclear reaction as a famous number 17.6 MeV. This, the functionality within PlasmaPy does make sure to check that a reaction is valid. So if we do something like deuteron plus triton, and then greater than sign to indicate the arrow, alpha plus, let's say 57 times neutron, so 57 neutrons. And what did I do wrong? Oh, variable name again, single neutron. Okay, we'll get through this. Oh yeah, this is the error that I intended to get. Good, okay. So we get an error that the baryon number is not conserved for reactants, deuteron and a triton, and products, an alpha particle and 57 neutrons. So, so it does check to make sure things like the baryon number and charge number are conserved, which is pretty helpful. Though one friend from the fusion community said that if this reaction was valid, then we'd have fusion power all set already. So, but alas, it's not. Those conservation laws. All right. Cool. I think we're doing pretty well on time. On AstroPy time, that is. Okay. I try. All right. So the next thing that we're going to do, are there any thoughts or questions on whatever it was I was just talking about? Cool. All right. We can proceed to some more solar physics-y, super magical, happy, fun things. Let's do from PlasmaPy.formulary import star and shift enter. And so we imported all of the functionality from PlasmaPy.formulary. And let's go ahead and calculate a few plasma parameters. So let's start with one of the more famous ones, so plasma beta, which is the ratio of plasma pressure, also called gas pressure, to the magnetic pressure. And this quantity really helps govern how a plasma behaves. So when beta is much larger than 1, the magnetic field isn't strong enough to feed back on plasma motions. So the plasma ends up behaving more like a gas, so something like a cloud. But when beta is much less than 1, the magnetic tension and pressure are the dominant macroscopic forces. So we get things like the really nice coronal loops and things that we saw in the SunPy tutorial. All right, so let's calculate plasma beta in a few different parts of the solar corona. And we'll use AstroPy units once again. So let's define B corona equals, let's say 50 Gauss. It varies a lot, but that's a good order of magnitude thing. And the number density of the corona equals 1E9 times U dot CM to the -3. So 1 billion per cubic centimeter. I have this written down. I wouldn't remember this offhand. And then the temperature of the corona equals 1 times U dot MK, 1 megakelvin. So now that we defined that, we can use those to calculate plasma beta. So let's do beta, and then T equals T corona, N equals N corona, and B equals B corona. And so we get that plasma beta in the corona is about 10 to the -3, give or take. It'll vary a lot if you're in an active region or not. But overall, the solar corona is magnetically dominated. Now let's dive down into the solar photosphere and get a few different plasma parameters there. So let's do T photosphere is about 5,800 Kelvin, U dot K. Regular enter. B of photosphere equals 400 Gauss. Again, this varies a lot. And then N of the photosphere equals 1E17 times U dot CM -3. And shift enter. And if we do that, we can get beta of T equals T underscore photosphere, N equals N underscore photosphere, and B equals B underscore photosphere. Then shift enter, and we get that plasma beta in the photosphere is about like 10 or so. So plasma pressure forces are a lot more important than magnetic tension and pressure, but not like overwhelmingly so. So magnetic forces do play some role. I used to have the chromosphere in here also, but nobody likes the chromosphere, right? Oh wait, unless you study it. Oh, I guess I study the chromosphere and I don't like it. So anyway, I have opinions about the chromosphere. It's a mess. I mean, sorry, the chromosphere is host to very rich and interesting physics. That you could probably better to quote me on. Okay, so the next thing we can do to stop me from talking about the chromosphere is calculate some plasma parameters for closer to home in Earth's magnetosphere. Let's use an example of MMS, the Magnetospheric Multiscale Mission. And MMS is a constellation of 4 spacecraft. And its goal is to study the small scale physics of the process of magnetic reconnection in Earth's magnetosphere. In order to do this, these 4 spacecraft have to be really close to each other. But how tight does the tetrahedron have to be? This is where we can use PlasmaPy.formulary to find out. And there are a couple of different plasma parameters that are important. And the first one is the inertial length. And what the inertial length is, so if you have a particle in a plasma and it's going around, the inertial length is the length scale it takes for the particle to get accelerated or decelerated. So if a particle is going to do like a 90-degree turn, then it's going to happen over a length scale that's comparable to the inertial length. And there's an ion inertial length and an electron inertial length. And both of these are important for reconnection. So the ions, so you have, in reconnection, you have particles coming in from both sides and then going out. And so electrons are a lot lower mass. They can do much tighter motions, but ions are like much more sluggish. They're a lot harder to accelerate. So let's calculate the inertial lengths of ions and protons in the magnetosphere. So you do n equals 1 times u dot cm minus 3. B equals 5 times u dot nanotesla. SRite units does take care of metric prefixes also, which really helps. And then let's do T equals 10 to the 4.5 Kelvin. So someone studying the magnetosphere and knows better parameters than these, let me know, since I use this example a lot. So shift enter. And invalid syntax. So I forgot an asterisk. Shift enter again. And so PlasmaPy has a function, inertial length. And let's say n equals n, and then particle equals p plus. And then to be consistent with the units that people tend to use in the magnetosphere, it's like kilometers. And so the proton inertial length is about 200 or so kilometers. So the ion diffusion regions in reconnection are going to be a few hundred kilometers thick. So let's calculate the electron inertial length next. We can do inertial length of n equals n, and then particle equals E minus. And again, let's convert it to kilometers. And another way that we can do that conversion is to do like u.km. So we can put in the unit object there directly. And we get that the electron inertial length is about 5 kilometers. We can also calculate the gyroradii. And I alluded to this earlier, but let's do this for both the protons and electrons at once. Let's live dangerously. Gyroradius. And so B equals B. And then particle equals, let's do E minus, comma, P plus as a list. And then T equals T. And with that, we can, again, convert it to kilometers. And we get an error. Oh, because I forgot to put this as a string or as u.km. And we get that the gyroradii of electrons and protons are 1 to like 47 kilometers respectively. So pretty close to the match ratio, it turns out. Or maybe exactly. Right, so the MMS spacecraft have separations of ranging from like 10 kilometers to hundreds of kilometers. So they're really well positioned to study magnetic reconnection in the magnetosphere. So yeah, we added the capability to calculate multiple things at once fairly recently. I think it's only like 2 years ago, sometime during March 2020 and March 2020. And it does make things a lot easier sometimes. All right. With MMS, it's also important to know like how frequently we have to take measurements. Because like if we take measurements too frequently, you still have to get a lot of that information down to the ground, and you can end up eating up a lot of bandwidth. But you also want to have resolution that's short enough to be able to like measure how things change. So let's do the plasma frequency and say n equals n, and then particle equals, let's do this again, P plus and E minus. All right, it's really nice how Jupyter Notebooks now highlight the parenthesis things that it really makes matching things easier. Let's do that. And we get these particular values. We also have a 2 Hertz keyword argument. I'll say true. So we can get that the plasma frequency is about 200 Hertz for a proton and about 9,000 Hertz for an electron. So these are the frequencies that we may want to take measurements on. There's also the gyro frequency. And that's B equals B. And again, particle equals P plus and E minus. And then 2 Hertz equals true. Okay, so the gyro frequency is a bit higher frequency. And then let's do the lower hybrid frequency. And so the lower hybrid frequency of B equals B, Ni equals N, and then ion equals P plus. Then shift enter. So I forgot the 2 Hertz. right. So it turns out that I can never remember what the lower hybrid frequency is, but most of the functions within PlasmaPy.formulary have descriptions of the physics behind like what is actually being calculated. So if we ever forget what the lower hybrid frequency represents, we can go to the documentation page and it'll give you a definition and then talk about the reason why the lower hybrid frequency is important. And this is true for most of the doc strings in PlasmaPy.formulary. One of the first times that I gave this tutorial, I mentioned this as an example of a place where people could contribute because we did not have a description of the lower hybrid frequency at the time. And someone ended up coming along and added this description, which was really cool. So open source is nice because we can draw upon the knowledge of the whole community. So, and so I never have to remember what a lower hybrid frequency actually is. Is that the one? No. I lost it. There. Okay. All right. And we're doing pretty well on time. I think we'll still finish early. And let's do a bit with ionization state data structures. So PlasmaPy has a couple of data structures to represent the ionization state distribution of a single element or isotope, or of multiple elements or isotopes. And in this case, for this example, let's just go through the first single element. And what I mean by ionization state, by charge state, is what fraction of an element is neutral versus singly ionized versus doubly ionized, and so on. So this case, let's create helium states as ionization state of He-4. And then I'm going to spread this out over multiple lines to make it a little easier to read. He4, and then 0.1, 0.7, and 0.2. So what this means is that 10% of helium-4 is neutral, 70% of helium-4 is singly ionized, and 20% of helium-4 is doubly ionized, so like alpha particles. And we can also add one more keyword argument in there too, an elem, and say that is equal to 1e7 times u dot cm minus 3. Okay, that looks all right. Cool, it worked. Okay. And now that we defined that, we can take a look to see what this object actually contains. So let's do he states dot summarize. In this case, it is a method, so we need the parentheses. And it's saying that for helium-4 0 plus, 10%, helium-1 plus, 70%, helium-4 2 plus, 20%. So the things that we put back in. And because we provided a number density for the element as a whole, and it was able to calculate the electron density, assuming quasi-neutrality, and then the ion densities for each of those. Is there a question? Could you use the microphone?
It's both of them. Yeah, basically, do you have to specify each of the percentages for each of the ionizing states? So basically, if you're working maybe with iron, would that look a lot more complicated then?
It would look a lot more complicated. I At the moment, I believe that we do need to specify all of the charge states. But this is a really good question because occasionally, like measurements, composition measurements from ACE are missing some of the lower charge states and don't have the capability to pick up neutral atoms to begin with. So in these cases, generally we set it to 0 and keep in mind. But one of the things that might be good to do is to set it as like not a number and then do the operations sort of assuming that, and that would help us keep track. So cool. Yeah, that is a good question. It has come up. All right. So now that we have helium states, we can do He states dot ionic fractions as a property. And we get back the 10%, 70%, and 20% that we provided to it. And we can do He states dot number densities. And because we provided a number density of the element as a whole up here, it was able to calculate what the different number densities are. And same is true for the electron number density. So He states dot n underscore e. And this is a bit inconsistent with like some of the other things that we do. So but we were able to get the electron number density as 1.1 times 10 to the 13th per cubic meter. It's also often helpful to be able to calculate things like the mean charge state or get what the most abundant charge state is, or sometimes the root mean square charge state. And with these data structures, we can do He states dot z mean and get 1.1. And He states dot z most abundant and get 1. So helium for 1 plus is the most abundant one. And it's a list because sometimes there might be a tie. And then He states dot z underscore RMS, the root mean square charge number, is about 1.2. And just like with a particle list, we can calculate an average ion. So He states dot average ion. And again, it returns a custom particle. All right, so these are the main functionalities. Are there any thoughts or questions on the ionization state data structures? Okay, so I will mention that one of the things that we do want to do in the future, and we have for a while, is to improve PlasmaPy interoperability with the HelioPythoniverse and make it so that it's easier to read in data from ACE, the Advanced Composition Explorer, into the sort of data structure. Because right now we don't have that capability. I think John and I have talked a bit about this. So hopefully before the next summer school, we'll be able to. So yeah, thank you for coming. We do have pretty thorough, we do spend a lot of time on our documentation. And we do have a gallery of like a whole bunch of example notebooks. And a lot of these are for like high energy density physics diagnostics. And then plasma waves, if you're adventurous, and then a whole bunch of things for the plasma formulary, including if anyone has dealt with plasma transport coefficients, I'm sorry. But also we have an example notebook covering that and things like Coulomb logarithms. One of the side effects I've had from contributing to PlasmaPy is now I have a lot of opinions about Coulomb logarithms, which makes you feel really grown up. But please feel free to check these out. And I believe that is it. Oh, we also have a contributor guide that is quite thorough and covers how to get set up to contribute, like how to set up a Python environment and things like that, what the code contribution workflow is, so like using Git and GitHub. And then other things like writing documentation and writing software tests. Software tests are the best thing since sliced arrays, I have to tell you that. So, all right, I think there was a question.
Oh, perfect. Is this okay? Do you guys have any plan to add anything for like secondary, like electron ionization, or like the formation of like lightning or streamer corona or anything like that, or like the modeling of kind of that side of plasma physics?
We don't have plans for that yet, but that would fall within the over umbrella of the software ecosystem that we do want to create. So yeah, I would be interested in talking with you more about that if you'd like.
Okay, cool.
Earlier you talked about an application of spacecraft propulsion. So from your experience of, in general, like plasma physics or of course PlasmaPy, what kind of properties of PlasmaPy can be used for techniques for spacecraft propulsion do you foresee?
At the moment, probably our general functionality would be most applicable. So things like the plasma formulary would come up a lot, or do come up a lot in plasma thrusters and Hall thrusters and things like that. We don't have extensive modeling capabilities. We don't have a simulation code within PlasmaPy. But yeah, overall, like Hall thrusters and also low temperature plasma physics are areas where we haven't had many contributors come by. And we would very much like people from these communities to help us create the functionality that is needed. So yeah, thank you for the question.
There are some folks in the industry who are using these kind of R&D techniques, but I'm pretty sure they're not aware of PlasmaPy, and even if they are, probably a very small percentage. So it's good to learn of PlasmaPy and you could spread the word around to those folks.
We've been trying. So the last APS Division of Plasma Physics meetings, we've had a table set up with like a giant PlasmaPy tablecloth and things like that, and like PlasmaPy t-shirts. So we were there for the whole week and we're able to talk with a whole bunch of people and raise awareness about PlasmaPy. And we held tutorials at that meeting also. But yeah, we do really, like, we're probably best connected into the heliophysics and high energy density physics communities. And there are a lot of areas of plasma physics where plasma science more generally, where we haven't had the contributions. And so, yeah, PlasmaPy itself is not feature complete, and we need the plasma community as a whole to help it help us get a lot closer to our goals. So thank you for the question again. Oh, microphone, yes. I almost said microwave.
Yeah, thank you for the great talk. Like the case of the MMX observation that you're trying to talk about, do you have any plan to make something like this for like the electric field generated from something like electric field to estimate the electric field?
Oh, I don't think we have anything like that in there now. But that would be, like, measuring the electric field, calculating that would be really useful. So yeah, thank you for that. I'll write that down. And if you have any functionality that you would like added to PlasmaPy, please go to our GitHub repository and create issues. And it's also really helpful to submit things like bug reports. We really do appreciate it. It is incredibly helpful to get feedback from the community. So yeah, thank you. Nine minutes early. Yes.
Thanks for day one, everyone. See y'all again tomorrow, 9 a.m., same time, same place.
Yeah, thanks everyone.
But yeah, I'm guessing it was somewhere in high speed as or just speed as in general.
Oh, sorry.
No worries.
Let me know what the paper was.
Sean, how do I stop the live stream? I forget what the option is.
I think if we killed the Zoom, it probably would kill it in YouTube also, but let's do this. Actually, never mind. Let's kill the Zoom first.
Yeah, kill Zoom first, but then we should actually shut down that instance so that Brian Thomas isn't calling the